if you can rewrite that in Julia without having to rewrite the entire Python code base, you can dramatically improve the life of everybody using this thing without having to convince whoever it is to rewrite the entire Python stack in Julia, as tempting as that might be. And on a similar line, of course, everybody knows Python is pretty highly entrenched in what many industries and also scientific domains. I mean, astronomy or biosciences are good examples. And it's not going away anytime soon. I don't mean to say that like I hate Python and I wish all snakes would die or something like that. But Python has a lot of mindshare. There's a lot of tooling available for it, and so whether you like it or love it, it's still going to be around for a long time. So it's worth thinking about how we can effectively integrate our Julia code with the Python code we want to end up interacting with. Okay. But when we're calling Julia from Python, there's definitely some new complications. Of course, this is true in any sort of language A, language B interaction, but we need to worry about how we share objects in memory, especially arrays. One especially important reason for this is that both Julia and Python are garbage collected languages. And so if we're sharing an array back and forth between Python and Julia, we need to be really careful about whose GC owns that array, when did the GCs run for various languages. We better hope that Python doesn't garbage collect an array we're counting on using later in Julia. So we need a careful way to mark things as dirty or fresh and ready to be reused. And we also need to worry about what happens, as we'll see later, when multiple Python threads start trying to call into the same Julia process, how well this works or doesn't work, and also processes like precompilation, which, of course, if you're having to precompile at the start of your Julia process, whatever it is, this usually involves threading. It can involve yielding back into this task scheduler and various other operations. So that's another thing we need to be careful about. And Python has its own sort of odd paradigm, if you like, when it comes to threading. So in older Python versions, as we'll discuss, there's this, I don't know if you want to call it like concept or phenomenon, called the global interpreter lock. So for each Python process, only one thread can be executing Python instructions at one time. This is the so-called GIL. And so in effect, Python threads running Python code are sort of like, I guess I was a little uncharitable by calling them fake. Or they're sort of like lightweight or fictitious, if you like, because only one operation is executing at any one time if it's pure Python code, but they can still be really useful for these asynchronous operations. For example, if you have a lot of different I/O operations, you can thread them in Python, so you can be like downloading a file in the background while another Python thread does something useful while it holds the GIL. Or you can also bypass the GIL by calling into a C library and you wait for it to do something, and while the C library is executing whatever it is, you've moved on to another Python thread that's acquired the GIL and you're like plotting something in matplotlib or whatever. But the GIL is something that is, if you're not using Python day-to-day, is a little bit odd coming from Julia, because of course Julia threads don't have this complication, but it makes calling into Julia code from threaded Python code a little bit complex, as we'll see. The reason this is a problem is, again, as I keep harping on, only one Python thread per process can be executing a Python instruction. So when we want to enter into some other language like Julia's codebase, we have to release or acquire the GIL as appropriate. So we can release the GIL and allow Python to keep doing its own stuff as long as we can guarantee we're not going to be touching any memory that Python owns. So sometimes that's really easy, right? Like if you are writing some library that just passes some simulation parameters, all of which are scalars, into your Julia code, well, that's easy because those guys are all just stack allocated, and you can just pass some ints or floats or whatever it may be. And then you can release the GIL and sleep happily because there's no risk that you're going to be touching Python memory. But obviously, this becomes a lot more complicated if you have some array that you're passing back and forth. So one technique people use to get around this, as we'll discuss further, is using Python processes, which also is horrible in its own way. Or you can even write Cython, which is for those people who aren't, I don't know if anybody's not familiar with this, but it's a lower level sort of C-like binding for Python, but effectively you have to write this sort of odd hybrid language and call into it and compile a bunch of .pyx objects, which also is kind of horrible. This was a big motivator for the invention of Julia, which kind of tells you like how bad it is. So happily for us, a lot of these complications are managed for us by the wonderful package JuliaCon, which has really nice support for working with Julia threads from Python. There's a nice simple interface for releasing and reacquiring the global interpreter lock. It'll handle initializing Julia for you and install all the packages you need when the Python wrapper module is imported for the first time. Of course, the package dependencies are only installed and precompiled at that first module import for what I'm sure is a very good Python reason that I don't 100% understand. But it's a little frustrating from a user point of view that the first time you install the module, you might be sitting there for 5 minutes waiting for everything to precompile. We can call Julia functions with a suffix that tells Python, like, hey, the GIL can be released, go do something else. And that allows us to explicitly flag, like, this code is safe to run without the global interpreter lock, or vice versa, like, nope, I gotta hold on to it when you call into Julia. And again, just to reiterate, this suffix means that you better not be interacting with Python's memory functions at all without relocking the GIL, which you can do from Julia code if you really have to. Okay, so hopefully I've sold you on the fact that it's definitely possible to call into highly performant Julia code, but there's obviously some complications we gotta worry about. And one big one is that JuliaCon is really great. It's a very smartly written package, but of course, like, it can't protect us from every single programmer error, which isn't surprising because I don't know about everybody else, but I'm really good at coming up with new, like, highly creatively stupid errors that I can make. So the ability of human beings to come up with bad code that can work around what the wrapper package is trying to protect you from is basically limitless. And one example of this is if you are using Julia code that yields to the Julia task scheduler to allow tasks to run, you may need to yield from Python to allow the Julia task scheduler to start rescheduling tasks. And if this yield never occurs, then the Julia task scheduler is just sort of sitting there being like, dang, I have this really long queue of tasks. I wish I could schedule some of them. That would be so cool. But I'm waiting for a yield, and no one is yielding to me. I'm just still sitting here waiting for a yield. It's a little bit like, I couldn't get a nice picture for this, but if you pull up to a four-way intersection and there's another person across the street and you're like, you go. No, you go. And just no one ever goes anywhere. And so you can inadvertently end up causing the Julia process to effectively enter a deadlock if you can't yield from Python into the Julia task scheduler. And you have to do this occasionally on a repeated basis, and it's kind of an open question on where and how much to do so. But this is a risk that you can hit even at the module import if you're doing something foolish, which I often do. So I've hit this problem where at module import, the entire process locks up, and we'll talk about why. So when third-party libraries, like from Python, are trying to launch the Julia package wrapper, they can do that in a way that we as Julia programmers can't control at all. So an example of this is that some beautiful Python library that someone has written, I've given it the awesome name, some Python library, creates something called a thread pool executor, which is going to manage Python threaded workers, which use the Julia code. So a thread pool executor is basically like the foreman of the threads, and it tells these threads, okay, when you start up, here's some initial instructions you should run. That's this function initializer, and then you can pass some arguments to that initializer too. So that seems like an obvious place to say, like, hey, please yield into the Julia scheduler so that Julia can run all of its tasks. But the problem is, this is some third-party library in Python that's just like kicking off thread pool executors and may not allow us as the end user to say, here's what I want the initializer to be. For example, maybe they have their own large, beautiful initializer that they would prefer to run instead, and there's no way to put ours on the list. Whoops, the list of things to run. So it seems like kind of a dead end to ask every single third-party library in Python that uses the thread pool executor to allow us to yield into the Julia scheduler. And this is an issue because this is exactly the kind of behavior that can cause this sort of deadlocking where the Julia task scheduler never gets yielded into. For example, IBM's Qiskit does this. It launches a thread pool executor, and you have no control over how those threads start up. Just as an example, but there's other libraries that do this. And of course, you can go to these folks and say, like, hey, please, can you change this behavior? But there's a huge number of Python packages doing this. And ideally, we would protect ourselves so that these third-party Python developers never have to worry about the dumb things that Julia does starting up, or at least the dumb things that Julia programmers have done. Okay. And again, I just want to mention that there are internal functions during startup that can yield into the task scheduler. And this seems to happen just experimentally when I've tried this out more when JuliaCall is not run from a main Python thread. So it's kicked off from like again, a thread pool executor, and one of the worker threads, which is not thread 0, seems to get stuck waiting to yield. I'm not enough of a Python expert to understand why this is, but if anybody here really knows Python deeply, I would be very interested to hear an answer to the question of why this happens. Seemingly only when the thread number is 1 or greater, but okay. So one workaround to this is to use Python processes to do our parallel programming instead, if we're able to do so. Again, sometimes third-party libraries say no, threads only. We don't support the process equivalent of thread pool executor, which is process pool executor. But on our end, as the Julia wrapper library developer, we can use processes to protect ourselves. So just a quick summary of the difference in Python between processes and threads. I know probably you're shocked, at a JuliaCon, to be getting so much Python content, so sorry for that if that's a traumatic memory for you. So Python processes, each one has its own GIL. So that means, of course, multiple Python processes can be executing Python instructions in parallel, unlike the threads, where they're subject to the parent process's global interpreter lock. And the other really important difference is that Python threads can share memory objects with one another. All their arrays live in the same memory space. For processes, that has to be explicitly handled through a bunch of different constructs, like a multiprocessing queue or something like that. So processes, by default, don't share memory with each other. So we have to account for the need to pass arrays, for example, back and forth, or any heap allocated object back and forth between the processes. So again, just really want to reiterate that the risk here isn't just that we'll have our Julia threads stuck because of the GIL, where only one instruction is submitted to Julia at a time, but rather that we can deadlock the entire process as a result of this sort of task scheduler issue. So the workaround that I ended up using that worked reasonably well for me is effectively to say, on the left here, we've got the initial picture where we have one Python process, which is in blue, and the colors even seem to have shown up, which is astonishing. Then we have some Python threads in green. So these guys are all trying to get some work done, and they're all calling into some Julia process, which is managed by the overall Python process on top. And this is exactly the situation where you can run the risk of the interaction of the GIL and the yield issue locking up both the Julia and Python process, which is kind of inimical to getting any work done. So one possible solution is to say, okay, the Python process is going to launch another worker Python process, not a thread, which will own the Julia process separately. So now these two have two separate GILs, and they'll be able to yield into the Julia scheduler as appropriate, and then we can use some sort of message passing between them to execute instructions from these threads to put onto some consumer queue for the Julia process. So effectively, this is just some big producer-consumer construction, but by moving the Julia process out into a separate Python process, it allows us to avoid this issue where non-main threads seem to lock up on Python. And this is great because it means that third-party Python developers don't have to do anything. If we execute this correctly, they can just run Julia process wrapper code from any kind of thread, and it should just work. At the cost of having to do something kind of ugly under the hood. So there are a bunch of downsides to doing this. One main one is that we have to initialize this process pool for the worker process that owns Julia at the module initialization, which definitely could have some risk of data races. It's hard to share memory with the Julia worker process. We'll see why in a little bit. Also, this is my personal opinion, but the multiprocessing pool interface in Python is not cool. It's not great. I definitely, of course, I'm a Julia programmer, so I like the Julia channels interface more. And if multiple Python threads want to use the Python wrapper module, then we have to be a little bit careful to avoid creating new processes for each one, and rather allow all the Python threads to share one process. So here is a code sample. Hopefully this is visible in the back of what this kind of looks like. So you can immediately see there's some big code smell going on here, because there's the infamous keyword global. I feel like anytime you see that in Python module code, it's a huge red flag of something not good is happening here. So in our wrapper module, we import the pool, and we create some variable to store the pool once we've created it. And then when we set it up, we create one process to manage Julia, we call some function that sets up Julia, like it imports all of our Julia code that we need, and then we make sure that when the parent Python process exits, also the Julia manager process must exit too. So just check and make sure that all of the Julia process work has been finished and then close it. Otherwise, you'll end up with a dangling zombie process, which is not good. So then setting up Julia, we just make sure that we haven't already imported JuliaCall. And then we set some environment variables that are important to make sure that we don't segfault and that we get decent performance. And then we can just import main from JuliaCall and start importing our Julia packages. Hooray. So this logic would be run on the child process that is managing Julia. And then from this, we can call in and just make sure that we are sending tasks as appropriate to Julia from any of the Python threads. So for example, this logic right here shows how you can do this. I've given it the beautiful name of it runs some task runner. Again, you got the nasty code smell of a global. And this is the sort of syntax in multiprocessing.pool to run something on whatever Julia interface entry point we have. So you just apply whatever arguments you were given to that, and then you also maybe want some logic here, so some function to handle Julia errors so that you can translate them, for example, to the Python error types that Python packages expect. Because of course, most Python packages like SciPy or whatever it is don't know how to handle a JuliaCall.Julia error. So you may want to translate the error type back to like a value error or a runtime error or something else that Python understands. So this is just sort of a little sketch of how this is all set up. Yeah, and then the interface runner, which actually does the work, just calls some stuff in my package. And this is, again, running on the child worker process in Python. I've really given some very exciting names to a lot of these functions here. And the other problem that we need to worry about is just sharing memory back and forth. So multiprocessing does allow processes to return arrays from apply, and they can share arrays back and forth. The downside is that by default, this is all done via pickle. Python's pickle is great for some tasks, but it's kind of problematic if the array we have is really large or we're dealing with some custom types that pickle is not sure how to handle. This is, of course, like the infamous problem of serialization and deserialization, which I'm not going to claim to know how to solve in general here. But the problem with using pickle specifically is that it can introduce really high overhead for the inter-process communication, and this can kill you if you have a large 2 to the 20 sized array that you're passing back and forth between the two Python worker processes. So there's a really nice blog post that I have shared the QR for here that you can read if you're interested, benchmarking a variety of different approaches to get around this. One maybe obvious one is stop hitting yourself, stop trying to share giant arrays between these processes. But sometimes the end user wants the giant array, and there's really no way around it. So unfortunately, you can't always just tell people don't do that, even though it might be the best advice. Another option, which is the one we're going to take, is to memory map large arrays to disk and then load them back and forth from the various Python processes. Obviously, this tends to have some overhead associated with it too, but it's a little more convenient than using pickle and tends to be faster in real-world benchmarks. And then there's another technique that I won't go into that this blog post discusses called copy on write. And we'll just look very quickly at the mmap situation. So here's a nice example. Hopefully this isn't too verbose. Effectively, we just search through the results of our function, find anybody who's too big, mmap it to disk, and then return to Python the location of the mmapped file and how big it is. Python needs that information to read it back. And then on the parent worker process side, once we get that information, here are the paths, here's how big they are, we can just read back from the mmapped file using NumPy, whatever object it was that we had written to disk. So empirically, this does seem to help substantially with inter-process communication, but of course, the number one thing you can always tell people to do is just stop trying to copy large arrays. Don't do it. It's not good. But sometimes people want to do self-destructive things. For example, giving a talk about calling threaded Python and threaded Julia, so you can't always protect people from themselves. And so if you're looking at this and you're saying Catherine, this is really awful. There's globals everywhere, there's mmaps, I don't like this, it's really bad. I would say I agree. So this is a solution to getting around this problem of your entire process deadlocking because you can't yield into the scheduler because you were called in a funny way. I'm not claiming that the solution is particularly good or that it's like particularly good software development practices, but it did unblock me. So it has that advantage over doing nothing. But if you don't like it, I think that's extremely fair. And I should have warned people to like bring a tomato to throw and be like, this is terrible. How could you do such a thing? But if you would like to come yell at me later, that's fine. I understand. The good news is that the global interpreter lock is going away. So hopefully, no one will ever have to do this horrible thing that I did. So here's, again, a nice QR code linking to this post. It's a PEP about how CPython in 3.13, which is one of the newer Pythons, is going to be supporting what they call free threading, which is like for us just like regular threading. But it means that multiple threads will be able to execute instructions in parallel, which would be great. The problem with it is that a lot of Python packages need to opt into this. They may need to modify their code to support it. So it's awesome that Python is trying this out and they're working really hard to support it. And for really big packages like NumPy and SciPy, like there's a lot of smart people who are working on supporting this. They have also, like everybody's heard of NumPy and SciPy, so if they need to call somebody in to help, they can get help writing thread-safe code that can bypass the GIL, which is great. But of course, we know that the Python library ecosystem is very large. There's a huge number of packages, and a lot of people are using relatively smaller ones that don't have the experience or funding, let's say, to get someone in to help them write thread-safe code. So for now, this issue where the threading paradigms in Python and Julia don't play nicely with one another, partly because of the GIL, is still going to be around for a long time. And unfortunately, we may still be getting like complaints that your Python wrapper code just like completely locks up my entire system. Why? And telling them, well, tell the third-party library to use free threading. Wow. It's probably not going to be a solution for a long time. And the other thing to note is that for now, again, in empirical tests, three-threaded Python tends to have worse performance in some important cases. I can dig up some references on that if you're interested, but it's kind of a problem when we're asking people to do this on our behalf. So again, the short story is that the global interpreter lock, for better or worse, is still going to be with us for a long time. And people like me are still going to be writing horrible workarounds to get around it. So in summary, while the GIL is still present out there in the wild, like haunting us, we need a way to work around it. I presented a solution maybe, that uses a separate Julia controller process to work around this. And you may say, like, well, I think the cure is worse than the disease. I would prefer instead to just tell everyone to use Julia, which is valid. But in the case you can't do that, this is one possible option for getting around this problem. So thanks for your attention. If anybody has any questions, we have like 3 minutes left. So.
Any questions? So it's not exactly what you were trying to do, perhaps, but have you played with the other direction, having Julia start up first and running your Python process through that entry point, and then is it easier to go in that direction? Then you can set up some communication constructs between Python and Julia and maybe have better control over the GIL?
It's definitely interesting. I haven't tried this myself because the use case I had was someone many someones who are like Python users only. They don't want to hear about Julia. They don't want to know about it exists. So I needed some way for them to have an experience that like seemed like pure Python, but secretly like under the scales, if you like, it was Julia. And that's like kind of where all of these frustrations come from is, you have some end user who's using some Python library that's doing something wild with thread pool executor, and you can't control what this third-party library is doing. So like, how do you protect the users from having bad performance? Or even worse than bad performance, like their whole system just like sitting there at 100% CPU doing nothing.
So like with packages like BAT, where you have Bayesian sampling, and I may want to support some Python package like ultranest for nested sampling. Currently, I do this with PyCall, and it used to work with multi-threaded target evaluation in Julia. Now I just tell people you have to go to one thread. Now I want to switch to Python call, but it is now Julia basically calling into Python, calling back into Julia. And maybe within one process. And even worse, if people then want to use bat from Python, they will have Python calling bat with like the sampling algorithm, which will call Python around the wrapper, which will then call back into Julia, which will then call the Python target function. Is this at all feasible?
Probably not, which is again why I say this is like not necessarily the best solution. It's really targeted for my weird use case.
with the lock and unlock GIL macros and so on.
Oh yeah, so that I think is feasible, but then you have to be very careful because you're now like on this downward spiral of like who owns the GIL, and it's hard to reason about. And of course, it's sort of similar to the M mapping question, right? You can tell people like, well, just don't call back into Python, but like people love doing silly things. I mean, I love doing silly things, obviously. So yeah, I don't know if I have a good answer for you.
Can we get our next speaker setting up? And we have time for one more question while that happens. Or not? Yeah, let's give the speaker another round of applause. Sorry I was late. Sorry I was late.
No, you're good. Do you need the signs? I can ask you.
Yeah, the signs would be great. Because I was trying to hand signal you. And it worked, but... It worked. Okay. Our next speaker is Arno, who's talking about mixed model small sample.
Yeah, thank you. I'm Arno. I'm a freelance statistician, and nowadays big data, AI is all the hype. Particularly, this talk is scheduled in between multi-threading talks, so probably you guys are used to crunching huge amount of data, but my job is to make the most if you only have a small sample, a small data set. In particularly, Julia already has a very nice package for doing mixed models, but the inference, testing hypothesis, confidence intervals there are based on large sample approximations. And yeah, in this talk, you will see if we can do something better for small samples. Because I only have 10 minutes, I will just walk you through a case study to try to convince you that this is worth doing. Particularly, we will be looking at a wind tunnel experiment where we have a car in a wind tunnel and we want to measure the efficiency of the car, the fuel efficiency of this car in various configurations. And we can configure the car in 4 different ways. The first two things you can tweak is the front ride height and the rear ride height. And to do this, you need to shut down the wind tunnel, take the car out of the wind tunnel, disassemble the wheel of the car in the front or the back, put it back together, put the car back in the wind tunnel, and turn the wind tunnel back on. So that's, of course, a lot of work, a lot of effort, costs a lot of money. For this reason, we call these factors hard to change. The other 2 factors, the jaw angle and the grill tape, they're easy to change. The jaw angle is just changing the angle of this platform, and the grill tape is just putting a certain amount of tape here at the front of the car. To do that, you don't need to shut down the wind tunnel. Those are much easier to change. We want to test these factors in 3 different configurations: a low setting, a center setting, a middle setting, and a high setting. And in experimental design, it is often the case that these are encoded as -1, 0, and +1, and then we forget about the engineering units behind them. So you probably know from statistics that it is a good idea to completely randomize your experiment. So yeah, a completely random wind tunnel experiment might look like this, but then you can see here that for the hard to change factors, that they change after every run, which means that after every observation that you gather, you need to shut down the wind tunnel. This costs too much money. The engineers of the wind tunnel don't want to perform this experiment, so it might be a better idea to restrict randomization somewhat. And then we see the experiment over here, and in the statistical jargon, this is called a split plot experiment. And in particular, what we see here is that for the 2 hard to change factors where the wind tunnel has to be shut down to change them, here these keep on having the same value for 5 observations in a row. So the wind tunnel has to be shut down less often. And yeah, this first group of 5 observations is then called the first whole plot. This name whole plot, this comes from agricultural engineering, where these experiments were first used. So plot here means, it kind of refers to a plot of land. Even though that's not the case in practice in a wind tunnel. So then the engineers of the wind tunnel were okay with performing these experiments, and they gathered the efficiency data. And now we want to model this. We want to make a statistical model of this. However, yeah, when you are doing ordinary least squares analysis, the assumption is that all of your error terms are statistically independent of one another. And when you do such a split plot experiment where you keep the where you do not properly randomize after every run, then it is very dubious that your residuals are really going to be independent. One of the reasons why this might be is because, well, here in the first 5 runs, you use the same configuration for the car. So it might be that you want to put the front right height to -1, but yeah, your engineers only have a finite amount of precision, so they might put it really to -1.01, and then of course that same error is propagated to all 5 of these observations because you're using the same car, and then your residuals will not be uncorrelated. This is where mixed models comes into the picture. We see here that we want to fit a model with an intercept, some first order terms, and then some second order terms, so quite a simple statistical model. But to cope with this fact that we have these blocks in our data set where we did not properly randomize, we allow that the intercept is slightly different for each whole plot. And then on the right-hand side, you see the default inference done by mixed models. And we see here the estimates of the point estimates of all of your terms in the model, some error on that estimates, then some z-score, which measures how far away from zero this effect is, and then a p-value. So a z-score, that's always used in statistics when you have when you do large sample approximations. And then I want to draw your attention here to 2 particular p-values here, which involves terms only involving the hard-to-change factors. So here you have a p-value e to the -10 and a p-value 0.02. If we then move to a mixed model small sample, where we make this adjustment for the inference, we see here that this p-value changed from e to the -10 to only 0.002. So that's a huge difference. But you might say, well, okay, that's still a very significant p-value. But if we look here at this other p-value, it used to be 0.02, and now it's 0.08. So depending on what significance level you're testing at, this term now becomes insignificant. Another thing I want to draw your attention here is that for now that we are doing adjustments, we have to calculate a certain amount of degrees of freedom used in a t-test. So statisticians will probably cringe a little bit at my explanation of degrees of freedom here, but think of degrees of freedom as the amount of units of information that are used for a certain estimate. In an ideal case, you want to have a degree of freedom which is on the same order of magnitude as the amount of data that we've gathered. So we have gathered 50 data points. So here for the effects only involving easy to change factors, we have degrees of freedom of 31, which is good enough when you have gathered 50 data points. But when we look at the estimates involving hard to change factors, we see that we only have 4 degrees of freedom. So we are only using, let's say, 4 data points to get to this estimate of the rear right height, and this degrees of freedom is more on the order of magnitude that you have whole plots in the data set. So, and of course, yeah, in the z-test, you are kind of assuming that you have an infinite amount of degrees of freedom, and 4 degrees of freedom is very far away from an infinite amount of degrees of freedom. So I hope that kind of convinced you that doing these small sample adjustments is worth it in certain experiments. Are these methods used in practice? Yes, they are the recommended method by the FDA for bioequivalence testing. So if you want to test if some generic drug product is equivalent to a brand name drug product, you don't want to do a huge clinical trial again. You just want to do you want to gather a small data set. For this reason, these small sample adjustments are useful there. And in this world of bioequivalence testing, SAS really still reigns supreme. So there are some open source tools like in R you have LMR test, but yeah, I noticed that there was always like 1 or 2% difference in the results between SAS and R. So yeah, I reverse engineered what the difference was between these two methods, and I noticed that yeah, in SAS they were using the observed Fisher information matrix, while in R they were using the expected Fisher information matrix. So the Julia package allows you to choose the hyperparameter such that you can both recover the result from SAS and also from R. In this case study, I showed you how to do t-tests. The package also includes code for f-tests, but I have not yet decided on a clean interface for the user. So look forward to that in the future. Thank you.
We have time for one question while Kieran gets his slides set up. Okay. Let's thank the speaker again. And we are now back to our regularly scheduled multi-threading mini symposium. And Kieran is going to be talking about a library that Relational AI has developed for thread groups, task groups.
Task groups. Okay, good morning, folks. Can everyone hear me fine? In the back, bring it a little closer. Okay. Okay. All right. Task groups are essentially reusable worker pools. We use them in RAI's knowledge graph product, which you can think of as it's basically a server. It's a cloud database, right? So it is a very large application, about 700,000 lines of code. And you can imagine we start and run very large numbers of tasks, and therefore how those tasks run is of great importance to us. So why do we have a package like this? So Julia's current task scheduler, which is biased towards tasks that are created more recently than older tasks. This is not visible in the small scale, but it's visible as your number of tasks grows, and I'll demonstrate that. Now, when you are biased towards more recent tasks, then responsiveness gets severely hindered. So the way the task scheduler works actually gets in the way of our application being responsive and reactive. Additionally, although Julia tasks are pretty lightweight, they still carry some amount of overhead. And if you have hundreds of thousands of tasks, it is kind of costly in memory terms and in scheduling costs. Task spawn overhead is also not trivial. So let's dive right in. I think this probably is a little difficult to read in the back there. Fortunately, you don't have to read all the details here. This is also in the repository for the package, which we've just uploaded. In a nutshell, what's happening over here is that on the left, we have a little worker function which does some busy work that yields frequently. It's basically just calling hash over and over, and every so often it calls yield. We measure the time difference, and we record that. When the work is complete, we we sample the completion sequence, and we record that as well. On the right-hand side, you see the rest of the code, which is basically calling threads.addSpawn. We call this so this essentially is going to create 10,000 tasks, which are going to each do some busy work, and each of those tasks is going to yield periodically. So what actually happens over here is this. On the x-axis, you have the spawn sequence, and on the y-axis, you have the completion sequence.
which means bottom left is your first task, bottom right is your, on the right is your final task, your 10,000th task, and up or down is where your task completed. And you can kind of clearly see over here that apart from a few exceptions around here, a few things that completed on at a reasonable time, your very last tasks are the ones that complete first, and your very first tasks are the ones that complete last. And this is kind of opposite to what you want for responsiveness in a server application. So task groups to the rescue, right? So this is essentially the exact same bit of code. Everything on the left is the same. On the right, we create a task group. We create a synchronization construct for the task group called this job tree join. And then instead of spawning a task for 10,000 tasks, we instead use a task groups method called submit job, which calls the worker function over there. Apart from that, it is essentially the same. Instead of an @sync block, we call wait on this job tree join, which kind of tells you what the job tree join is. And then we run 10,000 of them as with the same. So here is the spawn to completion plot for using task groups, which is entirely opposite. As you can see, the slopes line's the opposite. And the earlier tasks finish sooner, and the later tasks finish later. This is a fairness. This is fairness that is relevant for us, very important in a server application, because clearly if you have a client or a request that comes into your server application, you want to process the requests in order and not process the most recent request first while the first request waits eternally. Now, it's not perfect. You can see there's many outliers over here. We are kind of working against the task scheduler over here and still managing to accomplish better fairness than you see out of the box. But at the same time, it's not ideal. If you're interested in more about this, I'm giving another talk in about 40 minutes, 30 minutes, which goes into this in far more detail, talking about fairness. But in a nutshell, task groups is what we currently use and originally wrote to try to work around this problem with the scheduler. So how is this actually happening inside? And I'm just going to go over this at a kind of a high level. This is the whole package is 2 files, not very big. You can kind of read the code for documentation. In a nutshell, what's happening here is we're doing admission control. So instead of allowing 10,000 tasks to be spawned at once, we only create a small number of tasks. It defaults to 256, or 4 times the number of threads. The tests we ran were with 4 threads, so there's basically only 16 tasks that are getting created. You can do your own quick and dirty admission control, which actually does help you. If you play with this code a little bit, you'll find that just using a counting semaphore and only allowing tasks in periodically actually improves the fairness that you will see in the schedule. But there are gotchas. Deadlock possibilities and dependencies between tasks make things very complicated. So we have those problems in task groups also. You kind of have to learn your way around it. So the other thing is that we're scheduling what we call jobs, which are nothing but closures on the tasks. We don't spawn a new task and then destroy it for every piece of work. We just schedule jobs on those tasks. Starting a job is much faster. I think an order of magnitude roughly is what we measured than starting a task. And obviously this is only really noticeable that when you get into the tens of thousands of tasks scenario. Of course, as I mentioned, you have to watch out for certain deadlocks, possibilities, a job. If you submit a job and that job starts another job and depends on that job, you can end up deadlocking. There's some comments in the code that point you at that. So, but with admission control and that fairer task scheduling policy, you can accomplish somewhat a similar result, but this is a kind of a nice, neat abstraction, small package that can be helpful. There are two three basic things that are in the package. One is this, there's nothing novel here. Everybody's probably, who's done any parallel programming's probably heard of futures or promises, especially if you come out of the ML world. A future is essentially just a deferred computation, and you create a future, give it a computation when you try to sample the result of the, I'm very short on time. So we have the task groups has a futures abstraction built into it, which are used within the task groups. You construct a task group, and when you submit a job to the task group, it returns a future. You sample the future if you need the result right away, but it is probably already completed. This is just a synchronization construct, very similar to AdSync, as I said. All jobs must be submitted with a slight variation on the standard submit job using the job tree join. And really, the code's pretty simple. Go take a look at it, and hopefully it'll be interesting. So time for maybe one question.
OK. And Catherine, can you start setting up? And we have time for 1 or 2 questions.
So I'm curious if you've benchmarked this against polyester, which tries to do a similar thing in a kind of scarier way. What's the overhead like? Do you know?
I have not tried to do this with, compare this with polyester. My understanding of what polyester is doing and how it does it is that it will be completely unusable for our application in particular. It is very focused on HPC and throughput. So it didn't ever even come up in conversations, but it might be an interesting.
Yeah, polyester basically takes the scheduler hostage, so it doesn't work with other things. I have a question about recursion. So if I have a job that wants to spawn another job, how do do jobs pass in as an argument? Because it's kind of like structured concurrency in some way, but like you get the job tree join as an argument, or is it like a scope value or some way of getting because I want my recursive jobs to participate into my current job hierarchy, basically.
Yeah, so that's probably a little more detail to get into that answer than we have time for, but we can talk about that a little offline. Yeah, OK. Thanks, folks. Sorry, Catherine.
OK. Hi, everybody. So for everybody, I guess, who was here for the previous talk and isn't too horrified at the thought of me talking about threads again, I'm going to be talking about things that were frustrating and annoying as I was using multi-threading in the last year. And I know this talk title sounds like this is just going to be a complaint fest, but actually I think the message of the talk is really hopeful because most of my complaints have been fixed in recent releases, which Gabriel will be talking about later. Hooray! So definitely stay tuned for his talk, which I believe is after lunch. So first, I just also want to start off talking about all the things that are really good about Julia Threads. Again, we have a lot of really amazing features that I think are actually very easy to take for granted, especially the fact that we do have dynamic and nested threading, and it mostly just works. Sure, there's some pain points, but overall, it actually mostly works very well. We have nice support for atomic operations, including for pretty arbitrary types. Working with stuff like channels helps promote good designs, and also the fact that channels by default are thread safe is very protective for programmers like me who are just kind of running around like a bull in a china shop, destroying everything. We don't have to use macros to do everything, so if anybody here is an OpenMP user, of course, OpenMP is also wonderful, but it's nice that we have some good constructs that don't involve using funky macro programming to get what we want done. And we also have had good enough coarse graining in threaded loops to protect us from some of the task overhead for a long time, which is awesome. So I think especially in comparison to some other languages, Julia's threading is in a really good place right now, and there's still room to grow. But I just want to start off by saying, actually, I think the threading situation is pretty good, which is why when annoying things happen, they're extra annoying. How could this happen to me? So there are a few pain points. One of the main ones, I think, which also Kieran was mentioning, is schedule thrashing. So I have a lot of weird use cases where I want to create hundreds of thousands of tasks. And even there, the coarse graining can help a lot. But A lot of them can be relatively short-lived, and this is like kind of the nightmare scenario for the scheduler because you have some overhead, of course, involved in setting up a task and then reaping it later. And we then have to schedule those tasks in an efficient way. And there's also not that much information I can give the scheduler of like, oh, you should try and run this one and then this one and then this one. And if you're me, it's easy to write naive code that experiences this anti-pattern. Obviously, there's more sophisticated things you can do, but it can be relatively easy to write something that runs decently on like my crappy little laptop here. But when I got onto an actual compute node, the performance is not as good as I might hope. So again, this has improved now that we've had naive coarse graining since like 1.8, but there's still some room for improvement, which we'll probably hear about later. And the task overhead can become really frustrating if you have like millions of loop iterations that you want to thread over or something like that. And again, calling back to earlier, maybe the answer is just don't do that, but for now, people like me are still trying to do it, and the overhead is kind of annoying. Okay. Another maybe anti-pattern that people often encounter, people being me, is I have some sort of weird nested loop like this, and I don't necessarily know what the size of the loop is going to be when I start running it, and I want to figure out like what's the most efficient place to like insert like 2 levels of dynamic threading or something like that. This can be hard to figure out, obviously, if like I don't know what the loop size is before runtime, and one solution is to just write like 14 different versions of this with like all the combinations of where the @threads macro could go, and then just dispatch to them with some decision tree. But that's kind of annoying. It would be nice if we had a good way to figure out like, hey, you know, this inner, like the middle loop is much bigger, so prioritize scheduling that first, or something like that. And it's just not that obvious necessarily like where exactly is a good place to put the nested threading macro. So this, again, I understand is like also a pretty hard problem because like how do you, as the Julia core language developer, like figure out what the person intended or like which loop really makes sense to dispatch over? But it would be nice if there were a way to either specify like the maximum number of workers or give Julia some hints about which loop should prioritize actually having multiple tasks spawned or which could be combined into one task. And there's other things, of course, we could do. We can try and collapse everything into one mega loop and then back compute the other indices. This is also an option. It's like kind of a C-like approach, I guess. But it would be great if the threading scheduler were a little more accommodating of people like me with this weird loop pattern. Cool. This may be a minor complaint, but I'm like a coverage sicko. I want to see coverage get to 100%. And this also, I'm very willing to accept that this might be a problem with the Julia coverage system. But you can see in this screen cap I took from CodeCov that the end of the threading block is not covered, and it should be, because like all the rest of the threading block was covered. And in several files, I have like 7 missing lines, but they're not missing. They were touched. So I would like, I don't know, the threading people to talk. Okay, well, then talk to Claire. I don't know, but somebody needs to fix this because it's hurting my heart. Yeah, it's because of macro semantics, but the point is my 100% coverage badge is being affected. And my mental health is suffering, so just keep that in mind. Threads 4 has a lot of sharp edges. Again, maybe the answer is, well, don't use it. That's the answer Ray gave me when I asked her about it. But we also talk about it a lot in base threading documentation and the manual, so it would be nice if we either didn't talk about it so much as a recommended option or made it nicer. An example is like you can't use nested for loops, which again like may not be really Threads' fault, but it's kind of odd that this doesn't work and you have to split it among 2 loops, even if you know N and M when you arrive at like this macro. And I just want to keep time for questions, so I'll keep it moving. But things are getting better. I guess that's what I wanted to end with. You know, start off with some nice things and end with some nice things. Again, I really want to plug Gabriel's talk because he's going to give an in-depth discussion about how much Threads has improved, including the overhead and scheduler issues I mentioned. And also, one other great thing about the Julia community is that we have this awesome ecosystem of threading packages that you can try out if you think Threads 4 is not that great. So Mason is going to talk about that in a little bit. Definitely stay for that. And then, of course, Kieran also mentioned task groups. And one thing that, of course, like we're all working on this together, means is that we can take good ideas from these other packages and incorporate them into base as we go. And also, I can bug Claire about fixing the lowering issue for my coverage statistics. Oh, so that was the last slide. So I guess we have time for a few questions. And Mason, you're next, right? Do you want to come set up?
let's give the speaker a round of applause and questions. Okay, all questions have been answered, apparently. Well done. Yeah. Next up is Mason with Oh My Threads.
Okay. For some reason, I've been having some. Yeah. Okay. We'll try a different laptop.
What was wrong? Because it was up there.
It was up. For some reason, the display, the live stream doesn't like it. I don't know why.
It's a camera.
No, the signal we have the computer going through.
Oh.
Where's the?
Right, do you see it back there on the screen? Anything? Okay.
Where's the HTML file? Manifest. No, it's HTML. Where'd it go? That's TLML. No, that's Tom.
It's in the directory.
Should have been in there. Okay, I see it in here. I don't know why it's not showing up.
Can you try copying it over again?
Yeah, so
Just want to present it and have the live stream be broken, or?
we might have to do that. I don't know. It,
We're going to try copying it over one more time.
okay.
Sounds good.
Did that work?
Okay, sorry about that. So I'm Mason. I'm going to be talking about a package that I developed with Karsten Bauer called Oh My Threads. So basically, just as a little bit of background, we can probably go over quite quickly. Julia has these threading primitives. The lowest level one we have is kind of spawn and fetch, at least at the user-facing level. And this lets you do all sorts of kind of crazy things like spawn exponentially many tasks, which can be very slow if you do it irresponsibly. Most of the time in scientific applications, people really don't want to be using like threads and spawn. They want to have some sort of loop that they're threading over and processing data in parallel instead of dealing with the details of these things. So they end up using this threads.addThreads macro, which basically just you put it on a loop and it magically parallelizes it. It will break up your data into chunks and then applies basically the loop body as a function in parallel. Now, this is like a kind of for each like situation where it doesn't really have any primitive for combining the results of evaluation. So people get all sorts of bad ideas. I'm not sure I've seen this one done in practice because people usually find out right away that this is the wrong way to do it, but one's first intuition might be to just create some accumulator in a sum and then update it in a threaded loop and end up with nonsense. So that one gets caught pretty quickly, but it's like, yeah, basically my point is just that we don't provide a way to accumulate values very easily. So the suggestion that came about, like this is even in the blog post announcing our threading infrastructure, is to create some temporary stores equal to the number of threads, and then in your loop, ask for the current thread ID, and then mutate that temporary storage. This one's especially nasty because it usually gives you the right answer. And so, but if you have something a little more complicated than your simple example, say you have some special number type that for some reason yields to the scheduler in the middle of calculating the sum of two numbers, then you can get messed up results. Because basically what's happening here is that the task was spawned on one thread, and then it yields, and then it resumes on another thread. And so it mutates the wrong store, and all your results get screwed up. So a couple years ago, Carson Bauer and I were having lunch, and we started complaining about @threads. And basically, the result of that was that we decided that it was easy to use wrong and not very flexible. So you're allowed to have one of those two, basically our concern was that there had been this package threadsx that was kind of the main thing that you could recommend people to use. Like, okay, this will mostly handle these things well, but threadx was getting more or less unmaintained. I was trying to keep up with it, but I was not doing a good job of keeping up with all the very complex infrastructure behind that package. We both had kind of slightly different visions of what we would ideally like to see multi-threading look like in Julia in the far future if all of our dreams came true. But we agreed that we could get at least 90% of what we wanted very quickly if we didn't try and be super ambitious with some big infrastructure plan and just made a little package that basically parallelized MapReduce instead of for each. So our hope was that maybe if we come up with some good ideas, eventually these can form the basis of some improvements to base.threads. Basically, there's two ideas in OhmyThreads. It's basically just we should parallelize MapReduce. This more or less comes from the transducers ideas. And we should take advantage of this great package, chunk splitters, and just use chunk splitters for users instead of asking users to figure out how they should be using chunk splitters themselves. So just because not everyone really knows what MapReduce is, it's one of these scary terms. Basically, for each is just saying, like Julia has these functions for each and MapReduce, and more or less what they do is like for each will take some function and an iterator, and it will apply your function f to each element of that iterator. MapReduce is basically like this, but with an accumulation step. So it has a combining operator op, and it has some initial value, and then you make your accumulator equal to the initial value, you loop over your vector, and at each step, you're going to update your accumulator with this application of f of x. So you apply f of x to each element, but then you update the accumulator. This might seem complicated, but you're probably familiar with sum and prod. And both of these are MapReduces with the plus operator joining together items or the multiplication operator. So the thing is that if you have for each, it's actually kind of hard to implement MapReduce well, at least in parallel. But if you have MapReduce, it's trivially easy to implement for each. So this is kind of a better starting point, in my opinion. So you can write a for each loop just like this. You basically make some combining operator that does nothing, and then you MapReduce with an init of nothing, and you're done. So MapReduce is nice because there's very easy ways to tell people what is safe to parallelize with MapReduce and what's not. And basically, all that you need to know is that you have to not care about the order in which your mapping function f is being called. Your reducing operator needs to be associative. So this means that you can't care if you add b to c and then add that to a, or if you do a plus b plus c. And then depending on the details of your parallel scheduling, you might also require commutivity because certain ways of parallelizing over data might reorder your data. But usually, like for instance, threads.threads, you own, or not threads.threads, but most schedulers only require associativity. So the basic interfaces we kind of developed for Oh My Threads is a MapReduce function, a reduce function, this is just without the F, a mapping function, because this is often something people also need. They just want, apply some function to every element of a vector and give me all the results. And then a mutating version of map, and also a tasks macro, because people like writing for loops. So if we go back to our yield example and do these nasty myints, do a t-reduce with plus over them, we end up getting the right answer. And the bad sum in this case was off by only 1. So you can see just how dangerous this is, because you can really test these things, and even if you have yielding, you can mostly get the right answer. So this tasks macro is basically tries to act like @threads, except you can do things like tell it, okay, I have a reducing operator that should combine each result. So this sum could be written as @tasks for x and v, set the reducer equal to plus, and then return x. And that's equivalent to a MapReduce. We have this tmap function, just parallelized map, return vectors. And then just like @threads, we have some scheduling options. And the scheduling options right now mostly reflect what's in @threads, but it's extendable. You can just define a new scheduler and define what MapReduce means on that scheduler. So I would actually really like to implement a task group scheduler. I think that's something I've wanted for a while. So basically, our 4 different schedulers right now, we have a dynamic scheduler. This is the default. This is basically like regular @threads. We partition your data into chunks, and then each task gets a chunk of data. We have a static scheduler, which is like that, except we pin each thread. We make each task sticky, so it's not allowed to migrate. And this can sometimes improve performance in throughput-oriented situations, but you can't nest these. So if you have a threaded loop and you put another threaded loop inside of it, the inner one can't be, or I think neither of them should be static. We also have a greedy scheduler. This basically means that we, instead of partitioning each chunk goes to a task, we put all the data into a channel, and then tasks are pulling data out of the channel. This, however, means that your data can get joined in different ways, in different orders, and so you lose this requirement of only associativity. So if you use this greedy scheduler, you need a commutative operator. And then we also have a serial scheduler, which you can just pass this as an argument for the scheduler, and it will basically just do a regular MapReduce. And this is nice for cases where you want to use the same API for threaded and non-threaded functions. Now, where this starts to differ from @threads is that all these schedulers are customizable. You have fine-grained control over basically how many chunks how much you're going to chunk the data and how many tasks are going to get spawned as a result of that. So you can tell it, okay, I want 20 chunks, or if you have Julia started with like 90 threads and you don't actually want your data to be parallelized over all 90 threads, you could just say like, okay, only parallelize over 4 chunks, and then you'll only have 4 parallel tasks running at a time, and you won't swamp all your threads with all this overhead. Alternatively to n chunks, you can specify chunk size. So this is you saying like, okay, instead of, I don't know how many chunks I want, but I don't want any of my chunks to be, I want all of them to be a certain size. You can also specify a minimum chunk size. This works with n chunks, and this is really useful for just saying like, okay, I want to parallelize this sum, but if you give me a teeny vector, please don't parallelize it. Just run it in serial, and then we can use the minimum chunk size to not spawn huge amounts of chunks. Then there's the split operator. So this basically tells it how the chunks are formed. So usually you kind of want your chunks to come, like you want the first item to be in the first chunk, the second item to be in the first chunk, and so on. but sometimes for load balancing reasons, for instance, if you're threading over a loop where, say, the first few elements you expect to take way longer than the last ones, then this sort of scheduling can be really bad for things like the dynamic scheduler. You might want the greedy scheduler, but that has more overhead. So just randomizing or like distributing each element to different chunks can give you better performance characteristics. And so with the round robin approach, basically the first element goes to the first chunk, the second element goes to the second chunk, the third element goes to the third chunk, and then we loop back. So the fourth element would go back to the first chunk and stuff like that. Round robin requires commutivity. And you can also specify, I don't want any chunking. So each point in the iterator goes to a new task or gets put into the greedy channel. Just a little note, sometimes one thing that makes it hard to work with high-performant multi-threaded code is that it's often type unstable because Julia's tasks are not parameterized on the function that they're calling or the return type of that function for somewhat good reasons. So if you fetch and spawn, just return the number 1, Julia's like, oh, I don't know what that could be. And so we basically somewhat sneakily use the return type function in the stable tasks package to recover this type stability so that like tmap reduce over some vector, the compiler knows what that's going to return. We only do this as an optimization. We don't give users access to these inference results. We don't change behavior based on the inference results. This is basically just used to create type assertions that, okay, we have a upper bound on what the type of this, what the return type of each task is going to be before we sync them and combine all the results. And this just lets us take information from one place and move it forward. And this only works in particular because tasks run in a fixed world age. If tasks could execute their functions in an arbitrary world age, then this would be out the window because then you don't know if the return types that you figured out before you ran it would be valid afterwards. A bit controversially, so Julia's threading primitives like spawn and threads and all this all work in terms of closures. So you can run into all sorts of funky issues. Like for instance, say you thread over a loop, you label some variable A, you sleep for a bit, and then you put A into your vector, you can get weird results. Like for instance here, this should be 1 to 4. All of these are just 3. What happened was that you said A was equal to 1 outside of this loop, and this had a backwards propagating effect into this function body. And so this was actually a shared mutable container and that was getting overridden in a raise condition, kind of like the first example with threads that I showed. So this is not really avoidable in Julia's design, but what OhmyThreads tries to do, hopefully this is legible, is we at least try and catch times where basically the closure being passed into any of our functions, we try and detect if there's a boxed variable in there, and we're going to throw an error for you. And try and give you some hints and links to documentation on what happened. This is controversial. It has a lot of false positives. There are tons of cases where it was actually harmless. But I kind of think that this is good to do because if you're using threads, you probably care about performance, and these box variables are probably going to be very bad for your performance and stuff like that, and it just causes very confusing errors. So we basically say that you have to opt out of this error by using this allow box captures macro, and we also provide a macro localize, which you could put in front of this tasks. You could say localize A, and it would basically wrap this in a let block that would bring A local to that thing, and then it wouldn't be a captured variable. Probably, how much time do I have? Okay. So I think the last thing I want to mention about OhmyThreads is just that we try and provide some support for task local variables. So this is if you have some mutable storage that you might want to use in the course of your calculation. So in this case, we have some like vector of matrices, or some vector of matrices, and we want to multiply them together and then sum up the results and put these all into a resulting container. So like the serial way to do this is kind of obvious. You pre-allocate some matrix C, and then you mutate C with the mul function, and then sum them up together. There's many different ways, depending on your use case, that you might want to parallelize this. Kind of our preferred way with OMyThreads that we try and make easy is we have this local macro. So you can basically say, okay, I have a local variable this is going to be stored in thread local storage, and it will just pull this out of the thread local storage. This is basically the initializer, and then it will multiply like this. And so this will get shared, but each task will have its own version of this C matrix, and so they won't interfere with each other, basically. And you can do this without the tasks macro, but it's not as nice, and it's actually also a little slower. But you can use this task local value structure that takes a function which initializes the task local value, and then you can access that task local value inside a multi-threaded function. Yeah, so that's all I really have to present today, but there's a lot more. In particular, Karsten Bauer did a really good job writing nice docs for OMyThreads, and it just, even if you're not using the package, it has some very good advice on how to think about and use multi-threaded interfaces. So I'd recommend checking that out. I've got a QR code for it here if you want to.
Great. Let's give a round of applause to the speaker. And we have a full 10 minutes for questions.
Okay.
No. Oh, okay, there we go.
At the start, you had said this covers maybe 90% of what you would wanted. What's maybe like that extra 10% that isn't there yet?
So I think like what I want is I want the transducers library to be better. And I've been working on trying to fix up some of the transducer stuff, but it's a very big job, and I don't understand it very well. So what transducers lets us do is like we could do some of these map reduce operations and compose in various complications. Like say, like we could have maps that have filters in them and efficiently parallelize over a filtered operator. Stuff like that I think is somewhat hard to support in the current way we've designed OMyThreads, but when you have all this extra infrastructure for transducers, you can do some fancier things. Yeah, that's kind of the main thing. The other thing is that I would really like composability of schedulers. So, so in the rewrite of transducers that I've been writing, like we have basically like, for instance, a distributed scheduler that can hold an inner scheduler. So you could say a distributed scheduler holding a threaded scheduler, holding a SIMD scheduler, and it would generate loops that partition the data, send each partition to different processes, and then on each process, it would multi-thread, and then on each multi-threaded sub-reduction, it would then use SIMD over that, and stuff like this. I mean, it's fancy. It's not that hard to do in some sense, but like we just wanted to get OMyThreads out the door.
One more. Does there exist currently, and should there exist, a system that OMyThreads can check whether it's already whether you're already in a threaded MapReduce and therefore not thread anything inside an inner MapReduce?
We don't have that. That would be kind of cool. I guess we could use a scoped value for that. I would kind of worry about the overhead. Yeah, I guess it wouldn't be much overhead to just set a scope value. Yeah, that's not a bad idea.
For users deciding between different threading packages, can you offer some high-level guidance on when to choose what, particularly if we're writing kind of HPC-type things that might not at least explicitly yield and don't think we're yielding, but maybe don't know if something below us is? Like,
yeah, I think if you're relying on the idea that your function won't yield to be correct, then I think it's just a ticking time bomb. Like because whether or not something yields is kind of can be a result of optimizations. I don't really understand what processes can or can't yield, and I think these things are also allowed to change. Like, I think dynamic dispatches, for instance, can yield. And
Allocations yield.
yeah, GC safe points yield.
The,
So
the compiler allows itself to put a yield anywhere it wants. Do not assume that you do not yield.
yeah, and so like you could, everything could be fine. You could update Julia, and then like some escape analysis fails or something, and then suddenly you have a GC save point, and it'll just yield. And yeah, so I would really recommend not relying on that. I think Oh My Threads is kind of your best bet if you want a package to manage this for you. But you can also write like you don't have to use a package for this. Oh My Threads is just trying to incorporate together some best practices that we've picked up. But I'm not an expert on this or anything, so I would suggest reading some of the docs and look, because like just spawning tasks, splitting up your work yourself, spawning tasks, and then putting the result in those, returning the result you want from those tasks is a really good way to do this.
But ThreadsX and Polyester, is there some pro con?
So ThreadsX, I think, doesn't really offer anything that Oh My Threads doesn't offer. That was like kind of a design goal, was that this would be the next generation of ThreadsX. Okay, so that's folds.jl has a GPU backend. The GPU backend is broken. And that's just because I haven't had time to maintain it. But yeah, I mean, like there are nice things about ThreadsX, but it's really, it's kind of bit rotting. Polyester really scares me. I mean, it is fast, but I don't know when it's just going to blow up in my face. So I try and stay away from it when I can.
So this, I mean, we have this in multiple domains and multiple applications, and it's at least not an easy problem to solve. And we have all these parallel solutions. Like, for example, Oh My Threads is kind of a mini Dagger in some ways. Can we try to achieve some vertical integration with this? Like say, oh, we put these things in Oh My Threads, and then Dagger can maybe use some of those primitives to build on, so we don't have all these parallel things, and then users use several, and then they
I would really like this, but this is one of the things that can make projects like this go from a month to implement to multiple years to implement, and this is why Carson and I kind of didn't tackle that. But I have been talking to Julian about maybe Dagger integration, like a Dagger scheduler or something like this. I think this is something that he's particularly interested in.
Quick question then. I assume, but just want to clarify, reductions are also parallel, right?
Yeah. So, okay. So the final reducing step is so basically we spawn a bunch of in the default scheduler, we spawn a bunch of tasks. Each task does a map reduce on their chunk of data, and then if you have n tasks, then we serially perform the last n reductions. So I think I did write up a scheduler that will do the pairwise reduction all the way down in parallel. I forget why it never ended up in the package. I actually couldn't really find cases that felt somewhat realistic where it worked. Even when I made like the reducing operator sleep for a long time and do weird things or do very heavy, complicated stuff like multiplying matrices, I found it very hard to find a good demo of where this was a good idea to do, and so I didn't. I think that was the main reason it didn't end up in the package, but
Okay.
but we should offer it.
I think so, because the HPC folks, especially when they're strong scaling things, the reductions can actually be a surprisingly large cost of if you're not doing them in parallel.
Yeah, I definitely agree, but this is mostly a distributed problem, and Oh My Threads is trying to stay focused on threads, but I think a satisfying solution to these things needs to incorporate distributed reductions as well. But yeah, we should have a pairwise reducing operator.
And one last question while next speaker sets up. Yes, it is. If not, let's thank the speaker again. And I believe this is our last talk before lunch. Let's hope Karen slides.
Okay. So hopefully, well, maybe everybody here was here for my last talk. Don't have to repeat my entire introduction, but very briefly, some of the context for this talk here. When Julia introduced threads and we added @spawn and such, at the time the entire focus was on high performance computing and supercomputing stuff, scaling things really high. Throughput was what it was all about, and efficiency. Since then, I now work for relational AI, and relational AI is writing a server application. Our parallelism is utterly different. We are not focused on processing large chunks of data with parallel loops. We have functional parallelism, where we have groups of tasks doing certain operations and other groups of tasks doing other operations, and they feed each other and communicate back and forth. The challenges are completely different, and what you want from your underlying parallelism is also quite different. And one of the things you want is fairness. So here's your server application to set context, right? If you squint a lot, this is sort of what any server application looks like. You have requests that come in. You have a processing pipeline, which 10,000 feet up looks sort of like our application looks a bit like this. We compile a request that runs in one task. Then we run some optimization on that, and then we feed that to a query evaluator. And that evaluator runs a whole bunch of tasks. Those tasks are basically going to operate on data, and so we have like this cache, this pager cache thing, which goes off to the cloud and streams in data, which it has a 3-level cache, so it comes from the cloud to local disk to local memory, and there's a whole bunch of tasks managing, fetching pages from the cloud, writing dirty pages back to the cloud, and so forth. So there's a whole bunch of tasks here in this pipeline. So the question you want to ask is, in what order should these tasks run? Especially when you add the other twist that there are multiple requests which come in at different times, and so there are tasks for each of these requests. So in what order should these run? And in what order will they run? So I will assert here and talk about both these points in more detail in the rest of the talk. So tasks should be scheduled in the order they become ready to execute. First in, first out for fairness. Now, I don't know that people will argue with this necessarily, because your last thing you'd want is when you go to the DMV to anybody who comes in after you gets to go first. So for fairness, you definitely want FIFO. And another aspect of fairness is that a task should get its fair share of runtime. It's especially annoying when you're behind somebody who takes 20 minutes with the representative that you're waiting for to talk to for 10 seconds. So both of these are necessary for fairness. Julia's current task scheduler, as I said, was not really designed and planned thinking about this particular aspect of parallelism. The current task scheduler is a priority scheduler. It uses multi-queues. I have all these citations over here. I don't have the clever QR codes. I have to figure out how to start doing that. But yeah, so it was inspired by parallel depth first scheduling, which is an approach that is provably cache efficient for parallel code. And as it says here, it was intended to be efficient in time and space, specifically for nested parallel programs, because one of Julia's key advantages is composability, where you can take different packages that are not even necessarily aware of each other and work and have them work together. So if you are starting a parallel loop in one package and you have a parallel loop in another package, then you want them to compose well and throughput to work well. So there's a lot more in talk you can look up on YouTube, shared memory parallelism in Julia. So what's the problem? The problem is that the idea was based on a research a research topic, parallel depth-first scheduling. Additional work is necessary to evolve this further, to improve our ability to actually achieve this depth-first schedule, and that work has unfortunately not really happened. So it's a priority-based scheduler. Tasks do, in fact, have a priority field, but we don't use them. And the reason we don't use them is because as soon as you introduce priorities into a system, you open the door to starvation. Your high priority tasks hog the cores, and your low priority tasks never get to run at all. And debugging this sort of thing could be a real nightmare. There are solutions, but we actually have to develop those to detect starvation and to deal with starvation, aging, and so forth. So right now, Julia's task scheduler uses this elaborate, very scalable priority queue, but we don't use priorities at all. Excuse me. But then the question that I only started asking in industry is our task scheduler actually fair? If you go back to our server application, how do those tasks get scheduled? What's the ordering over there? When we first wrote this, as I said, the focus was on depth-first scheduling, not on fairness. So partly due to these lack of development in depth-first scheduling, there's been a push now, there's an open PR on Julia to add a work-stealing scheduler. And this is, there's nothing wrong here. This is a well-known thing. There have been multiple languages that use this in the past. It's efficient in time, space, and communications. The idea is very simple. Each thread has a deck. It pushes and pops tasks from the head of the deck. And when its deck is empty, it tries to steal from the tail of some other thread's deck. There's aspects to this, but fundamentally that's what happens. Now here's the key here. If you push and pop from the head all your tasks, that's last in, first out. Last in, first out is great for locality because you're running your recent tasks. Things that task was doing are probably still in memory, so your cache will work pretty well. But it's terrible for fairness because your older tasks can end up waiting indefinitely if new tasks keep being added, right? Yeah. So for people who were at my last talk, this is sort of familiar. Perhaps it's the exact same benchmark where we have a worker function that's just doing a bunch of busy work, hashes, and periodically yielding. And then it prints its completion sequence running number. So we run 2000 only with spawns of this. And again, we see on Julia 1.10.10 with just 4 threads, you see this blob of spawn sequence to completion sequence, which is, again, more or less oriented in the opposite direction that we want to fairness. So on our build of Julia, which is a sort of forked, frozen at 1.10.2, but we backport a whole bunch of things. We have some things from 1.11 and such. One of the things we have done is make a change to this behavior. And that change, as you can see, has kind of completely changed the orientation over here, which makes our earlier tasks complete sooner and our later tasks complete later, but it's a bit blobby, as you can see. So what did we do? It's a one-line change. In fact, it's a one-character change. In this file, we go from a less than comparison to a less than equal to comparison. But don't do this at home, because there are problems. There are downsides to doing this. We do improve fairness, right? And this kind of goes into a bit of an explanation. The multi-queue is basically a bunch of heaps, right, sorted by priority. But of course, all the priorities are the same because we don't set priorities. So when you pop a task off the heap, you take the topmost task from the heap. You're going to start running it. Then you take the last task in the heap and put it in the top, and then you sift it down. This is pretty standard heap balancing, right? If you have a less than comparison over there, all the priorities are the same. So less than fails, and then the last task stays as the first task. If you have a less than equal to there, then it will percolate its way back down to where it started. So you get more FIFO ordering if you do this, but you're essentially moving a task, rebalancing the heap on every new task and on every task schedule, right? So that's costly. The Fibonacci, parallel Fibonacci example that everybody loves to show up over here is actually will demonstrate exactly how bad this change can be. With just the less than, you'll see pretty decent performance from Fibonacci. With less than equal to, you'll see terrible performance from Fibonacci because Fibonacci doesn't do any work. It's just spawning tasks, essentially. And every time you spawn a new task, you're doing this heap rebalance on one of the heaps, and so you pay an enormous price in terms of performance. So your tasks have to have a certain thickness, a certain granularity, large enough granularity for this to be worth it. And even then, you pay a bit of a penalty in overhead, but it gives you fairness. So this actually ends up reducing to the old trade-off, latency versus throughput, right? Often they're contradictory, right? Optimizing for one will hurt the other. And this is one of those unfortunate cases that we see with the current task scheduler. Fairness is not usually something we think a whole lot about in HPC, right? It's just throughput. You want to get all your work done. There's not a tremendous amount of ordering constraints. But for the non-HPC world in which I now live, fairness is a very important property. So one question you can ask is, should we just give up on task priorities? Why the heck do we have a priority queue if you're not using priorities at all? Then we just drop this multi-queue and we just use a fast scalable FIFO, and that will give us fairness. And that is definitely something to consider, but just FIFO is not enough for fairness. You also want that second property, which is the fair share of time. Right. So the scheduler switches tasks, notwithstanding Oscar's warning that the scheduler can switch at allocations, tasks can switch at allocations and during GC and such. Yes, it can, but currently it doesn't. Mostly a task will switch when you explicitly yield or when you make some sort of a blocking call which supports that kind of a thing, right? IO, waits, that kind of a thing. So if a task does not yield and does not make a blocking call, it can run indefinitely. If most Julia programmers have perhaps run into this if you're doing heavy compute stuff, that you'll find that a tight loop will essentially hog all your threads and nothing else will make any progress because you were cooperatively scheduled. If your task doesn't yield, then the threads cannot run any other task. So what this ends up meaning is that your tasks will take varying amounts of time. This is that person in front of you taking 20 minutes arguing with the representative when you just have 10 seconds of stuff to do and you can't get it done because it's not fair. So when fairness is lost, your application behaves terribly. And that is definitely not an acceptable state. So is there such a thing as fair cooperative scheduling? Well, theoretically there is. And any PL geeks over here would probably really like this paper. It goes into small steps, structural operational semantics to prove that cooperative scheduling can be fair. But in practice, it's not that easy, right? You could do things like say, hey, at every time we task switch, we check. This task we're switching away from, how much time did it use? Did it use its fair share? Did it use more? Did it use less? And then we tweak its priority so that we are trying to be more fair to the remaining tasks in the system. Unfortunately, as soon as you start doing priorities, we have that other engineering demand where we need to add some support for detection and mitigation of starvation, and we haven't got that yet. But it is potentially a way forward. So there are other approaches, and these are kind of what we are using right now at RAI, where you kind of approximate the fair share by controlling how frequently your task is. It's actually frequency you're controlling. You give a task more runs, and you're approximating the fact that it takes less time than a task which had fewer runs. You still have to defend against starvation in this sort of scenario. there's been some discussion about our thread pools. Now, there are people out there who love thread pools, and there are people out there who hate thread pools. And one could argue that they are not very composable. They're a little difficult to use. And even though there's been proposals for adding user-defined thread pools, it's uncertain whether we should double down on the concept or whether we should move away from the concept in Julia. But if we did have user-defined thread pools, we can sort of, through resource allocation, get some sort of control over how much tasks run. If you have thread pool A with 2 threads and thread pool B with 6 threads, you're giving thread pool B more resources, so it will run more tasks. And so you have some control over there. And then another way you can get a fair share is through preemptive through preemptive task scheduling, which is essentially the idea that it's what the operating system does, and it's what other languages have moved towards, which is the idea that you don't wait for a task to yield or to make some sort of a blocking call. After a certain amount of time, you just forcefully switch away from the task. Go did this, right? Go started with a work stealing scheduler, and there's a heck of a lot of unhappiness with the fairness offered by Go routines and how to architect applications to get proper FIFO fair behavior. And therefore, they introduced a rather elaborate mechanism. They still use work stealing, but they also have a global run queue. So the global run queue is a FIFO. Every new Go routine gets spawned to the tail of the global run queue. And every Go thread pops a chunk of Go routines off that global run queue and puts it into its deck, its local deck. But then it round robins through all the tasks in its deck, right? And the way it does that is through signals. So there's a sysmon that's watching the Go routines running, and it says, hey, this Go routine has already run for 10 milliseconds. Send that thread a signal, and that sig URG is sent to the thread, and then the thread has to then check if this is a safe point at which to do a Go routine switch. And that's not very simple, actually, because there are considerations for what is on the stack. There's a discussion about where safe points are, whether they should do safe points or they should do a conservative stack scan. In fact, there's a surprising amount of overlap between what you have to do for preemptive task scheduling as there is with garbage collection, which also does things like conservative stack scans, or at least the new one. If you attend the talk on Friday about the MMTK work, then you'll probably see a lot more about that. So yeah, there's a bunch of details over here. There's a lot of discussion. When Go actually introduced this, they wrote up a proposal for it, and you can see some of the documentation, which, dating back to Unix. Go look at the source code, and the comments will tell you what's going on in there. But Go took about 2 years from the proposal to actually implementing preemptive task scheduling. And that's with the Go team size, right? And Google's deep pockets. This is not something that we can expect to do in Julia in the near term, or maybe at all. And so don't hold your breath if that's how you're thinking to get a fair share. Some approximation of frequency of tasks is probably, we feel, the way forward. Pursuing priorities and actually starting to use them gives you some more control over fairness and task ordering. Work stealing might be fine for one class of applications, but for a very large class of applications, it is not fine, and we wouldn't want it. I believe Gabriel's PR that's talking about work stealing is in fact structuring it in the form where there's a pluggable scheduler. So you could potentially see a Julia in the future that you can switch schedulers depending on your use case. Not ideal, but it does not really seem like there is one scheduler to rule them all. Going with preemption also adds a bunch of overhead, just to throw that in there, because you have to actually do those switches. So there's no really happy answer over here. This is more like a kind of call to action for people interested in threading, people interested in this problem. We have not definitely got this is not a solved problem in Julia. There are many things not so great about how we run. Even the interfaces, as you saw in Mason's talk, is questionable. How things are ordered and how things work is another consideration that we would like people to pay attention to, and not just on throughput. And I am very brief with this talk, but I think that's that. Thank you for your attention.
Yeah, we have a full 10 minutes for QA. Okay.
Thank you. So considering this is a difficult problem, why not just lean into the OS scheduler a bit more? Like, there's overhead obviously, but the OS scheduler does fairness, you have priorities, you have preemption. The thread pool solution seems like a good approach that I can see. And you can use work ceiling for anything that doesn't need fairness for the research type jobs.
So the composability challenge is basically if you do not multiplex tasks and allow for the support of potentially tens of thousands of tasks, then you're limited to what the threads can do, right? There are 16 threads on your system. You can only scale so high. Even Linux won't let you create, I mean, it might, but I've never really tried to create 100,000 P threads. But you can create 100,000 Go routines, or you can create 100,000 Julia tasks. How well they work is a slightly different question. The second aspect is, it's pretty fundamental, I feel, to Julia's productivity and usability, this composability thing. There's not, I feel, sufficient emphasis on how powerful that really is. The fact that you can mix and match packages from around the ecosystem and they just work, right? Parallelism is a great way to break that, utterly and completely. So I can go into a little bit more detail unless there's a bunch. But basically, if you're familiar with the HPC world, OpenMP and parallel for loops were utterly and completely broken if you wanted to use them in a nested way, right?
Yeah, the composability, I can see that argument. So we run a company where we have a lot of large jobs that we run for offline kind of research purposes, churning big amounts of data. Fairness is not really a problem. And then we have real-time applications. And in the real-time applications, what we really want is more control over the scheduling and the threading, which is really kind of awkward in the way Julia is set up at the moment. And so that's the direction I was going. But thanks for that.
I'd love to talk after and hear more about that.
Hey, so this example with the custom fork of Julia with the custom scheduler, is that a feasible thing to do when, for example, I have a workload that's mostly like HTTP based, HTTP server based, where the tasks take milliseconds to run? Because I suppose that's the point of the fork, right? How much better is the experience in that kind of workflow with the fork?
Okay. So I put the big red warning sign over there, right? You could try this, right? But there's a reason upstream does not have this change. Okay, the standard behavior of Julia is good for most of the users of Julia today. Making this change could give you benefits. It gives us benefits, right? But in a lot of cases, it's actually going to hurt you. So I'm not, I wanted, that's why I put the big red sign. I'm not advocating that we make this change, no, right? Especially if you have very fine-grained tasks. You know, if something's running for a millisecond or less and then switching, then you're just paying a ton of overhead and not getting a lot of gain. I did not show graphs over here to show performance costs of fairness. I just mentioned them, and I will mention them again. There are performance costs to getting fairness. right? Most recent, last in, first out is great for performance, not so good for fairness, and FIFO is really the other way around. So you could try it, but like I said, there's a reason upstream doesn't do it.
So I was thinking about workloads that we have in high energy physics where you have a bunch of things that you need to do which are very much throughput oriented, and you have another bunch of things to do that you want to run in parallel where fairness is much more important, and you want to make sure that those threads get constant time slices through the task. And that's one area where at the moment we do use thread pools. I mean, this is actually in C++ that this is mainly done. And the reason is that you basically want to be able to split the scheduling priorities between the thread pools. Mm-hmm. So do you see that as a potential evolution that Julia could support? I mean, it wouldn't be the default, but it could be quite nice for a lot of problems. It's sort of like, I'm going to give 2 threads to this. Fairness is really important. Every other thread on the system, I want throughput.
Yeah, so that's the virtue of thread pools, right? That's the reason we should maybe double down on them. The problem is it breaks composability. Every package is going to say, hey, I want a thread pool with 3 threads, right? And I'm going to start all my tasks on my thread pool. Now, as soon as you have 10 packages doing that, you've run out of threads. So we need some way for an application rather than a package to control this. Now, what we've been doing is we call the application the guy starting Julia. That's why we've put the control of how many threads go in the interactive thread pool versus the worker thread pool. We put that on the command line, right? The package doesn't get to control it. The guy running the code gets to control it, the guy who's pulled the packages together. But you can imagine that if you're pulling an application together and you have 16 packages and you're going to have like 12 thread pools, how are you going to set it up? Just starting Julia and passing 16 commas is not the way. Then you're thinking, oh, I need a JSON file or something of the sort to specify how I'm going to configure my thread pools. It gets complicated, and it's not really very composable, which is the negative statement about thread pools. And I don't believe any decision is made. I'm certainly not going to single-handedly make any such decisions, but I don't believe thread pools. I've come to believe that thread pools may not be the way forward. It's rare that we can learn something from C++, honestly. Yeah, they're great for amazing perf, right? If I'm like I said, if I'm at Livermore and I'm strong scaling nuclear simulations, I'm going to write it in C++ and use OpenMP and have nanosecond barriers, but I'm not going to use Julia for that.
I mean, just as a follow-up, if no one else has got a question, we have run into these problems as well, where we have workflows where there are arguments about who the application actually is. So the experiment will say, it's my framework that's the application, but the simulation toolkit will say, but I'm an application too, and I want my own thread pool. And we've definitely run into problems where that's happened. So I do take your criticisms on board. Yeah. It's not an easy problem to solve, but it's a problem that we have, and it would be nice to foresee a solution of some kind that you could employ.
So I don't know if you were at my last talk, but that
I was.
Yeah, okay. So that is possibly, an evolution of task groups. In its current form, what we've put on open source is kind of very basic. It's really more for demonstration purposes. There's many improvements you can imagine to that. But that is a way in which you can use stock Julia and control fairness a little bit. So you set up a task group for the things which care about fairness, and you use, the remainder of, you use other tasks outside the task group to get your throughput. So it's a little tricky. It's not, there's no, as you know, there's no clear, oh, this is the way you do it. But as people solve these problems and can define abstractions which help them solve these problems, we can upstream those and make things better, hopefully. Cool.
Okay, let's give our speaker a round of applause.
Thanks very much.
And we are we have one more talk of the multi-threading symposium, but that's after lunch. So go get lunch, come back here if you want. There's also other talks happening if you are done with multi-threading for the day. But yeah, the next talk's Gabriel on changes to the scheduling system.
Okay, hello folks. How's everyone doing? Hope everyone's enjoying JuliaCon. I'm Gabriel. I'm a compiler engineer at Julia Hub, and together with Sam, another compiler engineer at Julia Hub, we're giving a little talk that talks about the scheduler, tasks, and threads. Even though we say threads don't exist, unfortunately they're there hiding. So I guess the first question when talking about the Julia scheduler or schedulers at all is why even bother with a scheduler? Why should we have a scheduler? What does it give us? Because we know what it takes from us. It gives a bunch of complexity in code to maintain. Well, the goal is to be able to spawn thousands and thousands of tasks, and that's simply not possible using OS API. So a very simple example is I wrote a very complicated piece of C code that spawns n,000 threads that do nothing, and then waits on them all. Yes, very, very significant piece of code, and I'm sure it looks exactly like the code you people write. And running 10,000 threads takes about 0.7 of a second, which is, I guess, not bad. And 100,000 threads, well, that takes 40 seconds almost. And that is if it runs, because on my laptop this runs, but I tried it on a big Linux server, and it just said, yeah, I'm not going to let you spawn that many threads, and errored out. And that is simply because that's not how the C threading model was built or how it's optimized to do. While Arrow says, so you can spawn 10,000 tasks, and that's 3 milliseconds, and you can spawn 100,000 threads, and it's 40 milliseconds. So it scales pretty well, and you can make that 1,000,000, and it doesn't hang or cause errors or anything. You might hit some start performance bottlenecks, but you're not hitting a wall. It's just getting a little more difficult. And to talk about the task, we should talk about the life of a task. I thought there was a cool abstraction to see all the things that a task may do that may make it faster or slower. And unlike some other people, I don't like generative AI, so you're seeing my beautiful hand-drawn art. And the first thing about a task is, well, its creation. What is a task? What is the task object? Well, the task is that you can see that big blob of C struct. That's a Julia task. Those are all the fields that a Julia task has. That's everything that GC has to allocate. That turns out that's actually quite bulky. It's 224 bytes just in memory. So if you think, oh, I'm spawning a million of these, you have, well, 224 million bytes in task. That's not insignificant. And there's also things that are not shown on this struct that are pretty significant about the size of a task. So when we store the task for waiting on something, we actually have something that's called the state of the task, which is all the registers and everything. And those are actually quite big. And until, I think, less than a year ago, those were actually part of the task struct. So the task used to be, I think, 360 bytes. So that's one of the recent improvements Jameson did that just saves us a bunch of GC memory. Another big thing is the stack of the task itself. Well, the code has to be able to push into something, and we usually use mmap to do that, which we say is free, right, because it's virtual memory, so if you don't touch it, you don't pay for it. That's not necessarily true, but you can kind of think of it as being true, except OSs don't like doing 1,000,000 of these as well. So especially on Windows, I believe the number is around 10,000 of these that you can do in the process. That's not that many tasks. So we have a fallback operation when mmap fails, where we just allocate a GC object. And unlike mmap, that's much less free. That's actually reasonably costly. And, well, I now have a task I created. I went there and I did the task constructor and put a little function that does nothing on it. How do I execute it? Well, this is where the scheduler first shows its ugly head. You go and you call schedule on it, or do add spawn, add threads, or channel with a function. There's plenty of ways of creating a task, but they all eventually get to this function, which is called enqueueWork. EnqueueWork is the main part of the scheduler that takes tasks in. And you can look at the function that's actually quite complicated, and it's very annoying that it is quite complicated, because about 90% of the code there actually almost never executes, but you pay a cost for it anyway, which is Sticky tasks, for example. You may have heard people complaining, oh, you should not set sticky tasks, so sticky tasks are annoying. Well, why are they so sticky? What's the issue there? Well, when you use add async or just create a task by default, by the way, there's a new warning there, and you should, if you're just creating tasks and scheduling them, do note that they default to being sticky. It's a very unfun thing to discover. Well, like, why am I only using one thread? And then you discover it's because you forgot to set the sticky bit. Well, the idea is that every sticky task cannot run concurrently to other sticky tasks on the same thread. It's almost like by setting the sticky bit, you create a one-thread thread pool for those tasks. And we have to manage that everywhere, and it's viral. So if you spawn a task from a sticky task, or you take a lock with a sticky task, tasks around it start becoming sticky as well, which is fascinatingly awful. And it just adds a bunch of complexity and overhead. Like the scheduler has to take care of it. The scheduler has, and that outside of its own queues, which I'm talking about a little later, it has a queue for each thread that's dedicated only for sticky tasks. So this is one of the places where we just lose performance, and there isn't much that can be done without a breaking release. That would just either turn add async into not doing what it says currently, or just removing it outright. So let's get to, well, actually scheduling a task. So what is Julia Scheduler? So Julia Scheduler is what we call a cooperative M2N scheduler. That's a lot of words. We'll get to each of them. But the big thing is you have M workers, usually in Julia OS threads, so a P thread in most cases, and N tasks. That is very different from a normal OS scheduler, which is what we call a one-to-one scheduler, where you have a piece of work and a thread, and they're intrinsically attached to each other. This allows us, for example, to execute 1,000 concurrent pieces of work with only one worker. You can't really do that using normal C APIs. Of course, there's thread pools and Intel TBB, but they're all versions of an M2N scheduler. And the important thing about the scheduler, what it needs to do is, which task should it choose to run? Well, that's a great question. How do you choose that? And how do you choose that as fast as possible, because you don't want to waste the user's time deciding which task to run? Because you could get very fancy and say, oh, I want every task to run 10 milliseconds, and you measure how much time the task ran, and then you compare it with the other task, and you look through every task, and be as fair as possible. Which is great. If you went to Kieran's talk, you saw how great a fair scheduler can be and what its advantages and why we should really want one. But it's not free. So like, it's actually, in fact, at odds with being free. If your scheduler, for it to be the highest performant possible, if the only thing you're measuring is throughput, you want it to be as unfair as possible. Because if you just spawn a task, it means it's in your cache. Everything is right there and hot, so you want to run it immediately. And if it spawns a task, you also want to do that. But that's, as Kieran helpfully said, that's not how you actually want to do, because it means if you spawn a task to respond to an HTTP request 50 milliseconds ago, it may run only 2 seconds in front, and then it times out and nothing works because your latency is bad. So moving back to the current Julia scheduler. So the current one we have was implemented, I think, by Jameson and Kieran almost 10 years ago, it would be. And it's based, it was initially written in C, and now it's written mostly in Julia. It's based on this paper by Blalock et al. And the paper basically describes having multiple queues and task priorities. And you pick random tasks from the queues, and if you compare their priorities, eventually you have what they call a provably efficient scheduling for languages. Well, as you may know, our scheduler is neither provably efficient or very efficient at all. And one of the reasons is we just don't set task priority. So the big thing about the scheduler that's implemented is, well, you use priorities to do the nice things. Well, the priority is almost always 0. So there's a bunch of code in the scheduler that you're like, oh, look at the priority of task A, look at priority of task B, see if one's greater than the other, and it's always equal. So you're just doing a lot of extra code and a lot of loads and comparisons that you kind of already know the answer. So in essence, our scheduler, while it's implemented to be a really cool and fancy scheduler, what it actually boils down to is you have a set of queues that have locks on them, and you look at random queues, and you do a random comparison on these queues, and you just pick one at random. That turns out to be not a great choice. Well, one, you get a lot of contention. Our queues are not fancy lock-free, work-stealing queues that you might see. They're just basically an array with a lock in front of it. So, and the lock there is not very good. It's just a spin lock, which makes it even worse. So yeah, we should strive to change that. So we're going to get to that again. But let's assume we have scheduled. What else is there to do to run a task? It's part of the overhead. It's not just the scheduling. Well, you have to run the task. How do I run a task? Well, you have the current running task, and it has its own stack, its own registers, and all of that fun thing. And you can see all the piece of code there. That's actually not the entirety of the code that does a task switch. There's a missing function that could not fit on this slide without making it unreadable called context switch. This is all the things that have to happen for you to have a running task, store it in a struct, and switch to a new one. The operation boils down to, for those familiar with, to a set jump and a long jump. Set jump stores your current state. Long jump switches you to the new one. And this is all kind of expensive, and we try to make it cheaper. But it is part of, especially in some algorithms where you're, as Kate was saying, oh, I want to spawn 1 million tasks and run them with 1,000 CPUs. Like, if your tasks are very short-lived, these kinds of complexities that we have here actually do take some significant amount of time if you're not doing much work per work unit. Another important thing is waiting. How do tasks wait for things? This also takes time. So this is where Julia has one of my pet peeves, and it's kind of difficult to solve, which is there's a race that can happen between a task saying, hey, I'm going to wait for something, say another task, and calling wait with no parentheses. So the first function is usually called wait2 unqueues you into another task. And then the wait with no arguments tells the scheduler to find something else to run in your place. There is a piece of time between the first one and the second one. This is not an atomic operation, which means that we have to have a bunch of complexity for every single scheduler operation, be that a lock, yielding, and to make sure that we handle the fact that you can, for example, while in the process of waiting for a lock, someone might say, hey, it's your turn to run. What do you do? And we have to handle the fact that there might be 2 instances of the task in the scheduler and not do wake-ups at the wrong time. And it just adds a bunch of complexity that the scheduler has to handle. And, of course, it has a cost. And at the end, it's actually very simple to wake up a task. You just call schedule on. And again, so if you're unlocking a lock, you just go on its queue and you choose, hey, you're the one to be scheduled. And again, fairness comes here. Which task would you choose to wake up is actually a really important question. You may choose the one that was the last one to arrive because it's the most likely one to be in the cache and the most likely one to run fast. But now you're being unfair, and the one that's on the end never runs. And just before the task is done, it calls the task done hook, which also adds a little more code that needs to run for every single task you call. That before it exits, it has to wake everyone that's waiting for it and go look for work. And this is all like a task that does nothing, or just at least waits for something, has to execute all this code just to do nothing. So this is where like getting the overhead down is difficult, and you have something like Kieran's task groups where you can kind of skip some of the parts around this by choosing to say, hey, you have to be careful with deadlocks and have these tasks not depend on each other, because you can kind of skip some of these parts. And before the end, well, the task may get to a point where there are no more references to it, so it's going to be garbage collected. But it being special as a task, it still requires special handling, even a garbage collector, because while the task object itself is a plain GC object, well, you still have to free its stack. I also included a very good meme, which is, was this a good task? And the answer is no, because it used thread ID. And you should not use thread ID. It's wrong. Bad. So yeah, So I guess we get to like what needs to be improved. So the current implementation of multi-queues shows very high contention in a couple benchmarks that, while not representative of real workloads, stress each part of the scheduler in a runtime sense and a throughput sense, like Fibonacci or recursive IU. They're both like pieces of work that just each task is going to spawn more tasks, spawns more tasks, and you eventually spawn thousands and hundreds of thousands of tasks that all wait on each other. So this basically thrashes the scheduler. And the current implementation, you see if you profile it, I should put a little link, it's basically all spent in spin locks inside of the scheduler. And that is because the current implementation does not use a lock-free data structure. There's also the extra overhead of the insert of the non-atomic queue insertion and sleeping. There is a solution for that. It's called a parking lot thing, which the WebKit folks implemented and kind of everyone copied. It's a bit like a user space Futex, if that means something to people. We also have the fact that it's a cooperative scheduler, which means if your code wants to do a bunch of numerical operations and never yields, you basically take the task, hostage for your whole execution. And that leads to unfair execution. And there's several things we could do here. One of them would be preemption. Preemption would solve a lot of the issues we currently see, but it's a very difficult implementation that requires lots of details, and we just haven't gotten to it. And we may eventually do, or we may not. There's trade-offs to it. One other thing is Julia still has a couple concurrency issues that we know are laying around, and sometimes they rear their ugly head. And it's like, oh, my code stopped working for some reason. And it's like, oh, let's see if this person implemented something wrong. And you see that their code is perfectly fine, and you figure out, actually, no, this is our fault, not the user's fault. So this is something that we're currently working on. We'll also get to a little bit later. But we can also say about the things that have improved. One of the big things was that Julia can now compile things in parallel. You may have seen if you spawn tasks that do compilation, which is pretty common if you're, I don't know, responding to server requests that do arbitrary things. There used to be a big lock around compilation and codegen that made it so everyone waited on it, and it was a non-cooperative lock. So not only was everyone waiting on it, the task that was waiting on it could not do anything else. So it ground execution to a halt, and that is on 1.12 fixed. If you have many tasks creating compile workflow, and that, it does scale. You can look at it, look, that's not linear scaling. Sure, but it's better than what it was before, which was no scaling at all, or just very little scaling. One of the big things also in 1.12 that allows us in the future to make improvements to the scheduler and many of these other things is atomic memory. So before atomic memory, there were some atomic operations that we just couldn't really express in Julia without using an external package like atomic.jl, and that package didn't handle all cases that we might have wanted. OneSpur is also useful. We're talking about thread ID. One of the solutions to not using thread ID is just having a once per task that allocates a little piece of memory, and that works great. So future current work. So the first thing I think will get merged, because this could get merged today and nobody would complain, is pluggable schedulers, which is the scheduler itself has a pretty simple interface. You put tasks into it, you get tasks out of it. That's all the operations a scheduler needs to do. And currently in Julia, the way it's not implemented as such, there's 2 or 3 weird ways of doing it. And that PR 56475 basically coalesces them into push and pop. Another PR I have is implementing work stealing, which is a completely different scheduling logic. It's very common for, if you look at OpenSilk and OpenMP, some types of OpenMP schedulers are work stealing, which specifically in the implementations, there's 2 separate implementations that are there. There are no locks inside of the scheduler, which is great because you can't contend on those locks, though you can have contend in atomics, which still slows things down. This is future work that we've been wanting to do, is implement a parking lot style of concurrency primitives in Julia. It would simplify a lot of one, the concurrency primitives themselves, and two, the scheduler, which probably allows us to make it slightly faster, just less branches. And I should have changed the order here. One simple thing is just renaming base.threads to base.tasks. The name threads is wrong. It doesn't mean what it should mean. And like threads are not an abstraction that's exposed to the Julia user unless you use APIs, which you should not use. So like why have the name there? It just confuses users. So it should really just be base.tasks because that's what it's actually doing. And the final thing that I want to talk about is sanitizer support. So currently in Julia, you don't really have a way to know if your threading code is correct and has no threading bugs, unless you go and look at it a bunch and think about it. But that's not good. And you also don't have that much deadlock detection. There's just a couple things that try and detect deadlocks. But because we're an LLVM language, we can harness the power of thread sanitizer, which is why I brought San, which has been working on TSAN lately, to talk a little bit about it. So here, go ahead, San.
Hello. So I'm here basically to deliver the message that sanitizers are very cool, and we should be using them more to work out all the issues in base. So thread sanitizer is this thing that lives in LLVM now, and it does this magical thing, which is it can detect data races, even if when you would normally run the program, that data race might not actually result in any misbehavior. So there's a lot of code in Julia now where it has data races, but we don't know because it's so infrequent that you might not even recognize that that was the source of some kind of bug you ran into. So I have a short explanation about how thread sanitizer works because I thought it was very cool. And then I'll show you an example of a bug that we found with thread sanitizer and how the reports look. So the way it works, and this is going to explain a lot of the slowdown. So there's an expected slowdown of maybe 10 times when running with thread sanitizer, and you need quite a lot of extra memory to do it. So in this example, I have two tasks, T1 and T2, and I've got one variable that they're going to be fighting over on the heap. So what thread sanitizer does to keep track of things is, first of all, it gives each of these tasks a vector clock, which is a very cool technique, and I'll get more into about exactly how that works. But if you look on the left, what this represents is basically a time counter. So every time we do something, we're going to be incrementing a clock. And the way it works is that for T1, the left one is its own time, and the right one is the time that it observed from T2 the last time they synchronized. So what is synchronization? Well, there's a whole bunch of ways it can be done, but if you imagine that T1 holds some kind of lock and then releases it, and then T2 acquires that lock, now they've synchronized. So we know that whatever T2 is going to do definitely happens after whatever T1 just did. So we can see how this works. First of all, T1 is going to write to X, and it's going to become X prime. So you can see that its clock incremented, but because T2 is not synchronized with T1, it doesn't see that increment. It still has 0 there. So if T2, at this point, were to go and read X prime, thread sanitizer would actually catch that as a data race. It would save an unsynchronized read from T2, because it will read the shadow heap, which is the source of a lot of the extra memory consumption, and say, oh, well, okay, T1 wrote this at time 1, and I only observed time 0, so we're definitely, I have not, there's no happens before. However, if we synchronize, T2 can observe the clock from T1, and now we can write or read to it, and we can observe that, okay, that's safe because it was previously T1-1, and now that T2 has touched it, it's going to be T2-1. And that's the basics of how thread sanitizer works. It's a very clever idea. And finally, I will leave you with an example of a bug we found. So if you run Julia with thread sanitizer and just like mash at the REPL, you can actually get this to come up pretty quickly. And all this is it's showing you, hey, there's a data race. There's a write of size 8 here, and there's a read of size 8 there. And you can see that there's T16 and T102. So these are actually Julia tasks and not processor threads. And it gives you a backtrace. What's really cool is that if you hold locks when this warning comes up, it will actually show you a list of locks that each thread holds, so you can debug issues there. And it will even give you a backtrace of where you acquired those locks. It does a handful of other things. So for example, it can try to diagnose deadlocks and a handful of other data release related things. It's very, very neat. So that is my message. We are working on getting this to be easily available for user Julia code, but there is a ways to go with actually making it possible to use base without having a flurry of error messages from TSAN. And that is all I have to share.
Thank you, Sam. And yeah, that was most of the talk. I want to give a pretty good time for questions. And yeah.
And question time.
When? Thread sanitizer.
The forbidden question.
Yes, yes. Even early access, 0.1 or whatever, it would be pretty awesome. Assuming there's a way you can mask stuff from base, it's kind of should be basic, but it would be so useful.
Yeah, so it's like there has actually been like the bare bones sanitizer support in Julia for ages, and it's just all behind ifdefs, so it's a huge pain to use. And we also didn't have an easy pathway of getting a system image that was instrumented with thread sanitizer. So I don't know if it's going to be like super easy to get access to, but pretty soon you should be able to run a command to actually build a thread sanitizer enabled version of Julia. And that should be not, it's probably not something you'll be able to get from like Julia up anytime soon.
Can I ask, just to follow up over there, a blog post or like a write-up on this would be even more valuable than, I mean, I can see the ifdefs in the code, but how you used it to maybe find that particular, okay, well, you described that, but kind of an overview of the process would be really awesome, so please.
Does TSEN have filter?
Yeah, so I don't know if you were asking a question about filtering or if you're already aware, but you can actually provide a config, a whole bunch of options to TSEN, which is like, okay, I don't care about this error, and you can suppress things, and there's a whole bunch of knobs you can turn.
Very nice talk. Thanks a lot. Is there any new interactions or niceties with interaction of scheduler and the garbage collection? Because one of the common thing is there are things that left over from the tasks that will just stay there forever.
So yes and no. So Kira implemented something that cleaned that up, but at least the first implementation of it made Control C. So if you go to Julian's talk, you're going to hear a lot about it, or watch it, I guess, about Control C, which went from very broken to if you press Control C, it kills Julia, due to very annoying detail of how Control C was like sent to a random task, and the way it worked was like it was sending to a task that was not able to recover from it and just died. So currently, that specific issue, I think the fix is in on the 1.0 or going to be master, but it's not in 1.12. We tried it in 1.12 and it broke lots of people's code. So we are now triaging. I think it's a pretty good implementation that's going to be on master, but basically the one of the issues there is the Control C handling of the task. And if we fix that, we can re-add Kieran's change that makes it so threads don't hang on to tasks. Okay, any more questions?
Okay, in that case, let's thank Gabriel and Sam again.
Oh, this is yours.
I have a message from Catherine, which is that I am supposed to tell you all that there is a keynote at 4 p.m. in the main room, and then poster session at the alumni hall at 6 p.m. where there will be food.
Where is the alumni room?
I do not know that.
Good.
And now we're off to Luca for chapel things.
Thank you. Yeah, hello everyone. I'm Luca Ferranti, and now I'll be talking about Julia Chapel interoperability. So this is a very simple demo, very work in progress, but I want to share ideas and a vision on what can be done and how can be done and so on, and have a small demo of something that actually even works. So, as I said, a few disclaimers, so early work in progress, so there are some results, but there's a lot of things that can be improved, and if you want to chat with me with the hackathon, if you want to play with me, sure, I'm always happy for playdates. We can hack for more things together, and I don't want to tell anyone you should use Chapel instead of Julia or stuff like that. If you know me, I'm pretty happy in the Julia community, so I come in peace, and I would also like to live in one piece from here. Yeah. And so maybe the most important part of the talk is that in 20 minutes after my talk, so after 2 talks, we are going to have in this same room a buff, a burst of a feather about Julia and Chapel. And we have as a special guest Michael from the Chapel team, so a core developer of the Chapel language. So if you want to learn more about the language or get answers to all the questions I cannot answer, that's a great place. So, my talk is like the small free appetizer, and the buff is like the 700 meal in the fancy restaurant. So come for the buff. Yeah. That being said, briefly about me, how I found Chapel, it's pretty fun. So 3 years ago, apparently, I was browsing Reddit, and I found this post about this coding day in the JuliaCon. So JuliaCon is the yearly conference about Chapel, and they had this tutorial that says, yeah, if you want, you can join, ask questions, and there's someone from the team helping you. And I did that, and I thought it was very cool that I had Brett, so the original author of Chapel, answering all my dummy questions. So very welcoming community, very small, cozy community, which is very nice, and so that's why I sticked around. I like the language. And what is Chapel? So maybe you heard this language. So it's a language which I think development started roughly about the same time of Julia, so roughly the same age of Julia. And it was mainly developed for HPC and parallel programming, and particularly for making parallel programming productive and efficient in terms of not CPU efficiency, but human efficiency. And in a way, what struck to me when I saw this is that I think Chapel spiritually reminds a lot the two-language problem that is well known in Julia, without though overlapping or competing. So just like in Julia, we want for researchers to give this speed of prototyping, getting research idea when you explore quickly without giving up on performance. The selling pitch of Chapel is that you write some Chapel code in your laptop, and then the exact same code can scale on multiple nodes, distributed programming, multi-threads, and so on. So making parallel programming easy to write, enjoyable to write. And this talk here is going to be Then first, other thing to mention is this graph that you probably saw a lot of times also in the Julia Slack. Fun fact, this is used by Julia people for advertisement because it does very good Julia, but it's actually originally from the Chapel team, as you can maybe guess from the small HP logo, if you ever noticed. So what this graph is showing that Julia and Chapel are both in this sweet spot of languages, where you have on the y-axis the time, so the lower the better, so it's fast. And on the x-axis, this kind of size of the code, so how verbose the code is or how concisely you can express things. And generally, you either get a lot of fast code, but in a very verbose, complex syntax, like C, Rust, and so on, or you get very synthetic code like Python, which is slow. But then Julia and Chapel are in this sweet spot, in this sweet corner together, ruling both, which is pretty cool. And so what I started typing a bit is can we use Chapel and Julia together? And why would we do it? Well, I was finishing my PhD thesis, so I needed an excuse to procrastinate. But other than that, if we think to one direction, why would we want to call Chapel from Julia, for example? Well, Chapel has a different approach to distributed computing, the way it handles it. So it could make for example, a nice alternative to MPI.gl. That's something interesting to explore that we'll discuss more in the buff. Welcome to join. Then if we think the other direction, why would we want to call Julia from Chapel? Well, objectively, Julia has a much bigger ecosystem, for example, for scientific computing. So it would also good for Chapel to, for example, rely on distributions.gl for sampling from distribution instead of re-implementing everything from scratches, or for using differential equation solvers. Yeah. And finally, the cool part, so a small demo of how to call Chapel code from Julia. Let's hope it works. Yeah. Okay, so here I have a very simple Chapel code. So if you have never seen Chapel, this is Chapel. I'm loading a couple of libraries. So this library sort for like sorting functionalities and C types, which is used for C compatibility. And then I'm defining two simple functions. One which simply adds 1 to an integer, and the other one which sorts an array. And a couple of comments. So this proc keyword is how you define a function in general. This export keyword is used to tell Chapel, hey, I'm going to use this function from C code. So the building block of this whole talk is that Julia has very good interoperability with C. Chapel has very good interoperability with C. So when you glue the two together, you get very good interoperability between Chapel and Julia without doing almost nothing. So this export keyword is to tell Chapel, like, hey, I'm going to use this from Julia, from C. And then these sorting integers, like I'm not, I don't think this is how in any ideal world it should look, the function. So here I'm doing a bit of shenanigans because instead of taking a vector, it's taking a C pointer for the reason that I want like to work it out of the box with the Julia C interface. So a pointer to an array, and then inside the function, I'm building the Chapel array from the pointer, and then I'm sorting that. And in an ideal world like this, I should not need to do that. Ideal world, I would just write Chapel code, and then some Julia wrapper would handle all these shenanigans on top of it. So now we have the Chapel code, and then what I can do, which I will not do live, is I can compile it, and I would normally compile it the normal way, except I will tell it to generate the dynamic library, so I like .so file, which I can call from C file, and the fast keyword here is to say like this is production, so not prototyping, so turn off some checks and so on. And after we do this, we see we have this SO file, which binary, which we could call from C. However, since Julia has already very good interface, it turns out you can directly call that from from Julia without almost needing to do anything. So this is my very simple prototype of Julia wrapper. So this function is some boilerplate that ideally nobody except me would need to write, where you need to basically tell the compiler, hey, I'm going to use some Chapel runtime, so you need to do some initialization. And then just with normal SQL, we wrap the two functions that we defined, this add one and sort integers. And yeah, let's run it. So now I have created it, and now, yeah, 3 + 1 is 4, so it works. Then for the more interesting one, let's create a vector, and then we do sort integers, and it sorts that. We can, like, I can do quick benchmark, but take it with a grain of salt because it's a miracle the projector works in the first place. But and also, so Chapel version. How much time do I have? Oh, 1 minute left. Yeah, let's see if I cannot. Yeah, and then we can do the Julia version. But to be fair, I'm not sure if this is the best way to benchmark. I'm not sure if in the Chapel version it's removing some time or function something, but it's just demo. So to conclude, while it runs, this is very early prototype, but if you want to play, we can play at the hackathon. It would be fun. And ideally, what I would like it to do, I would like to have like a better interface so that I can directly pass Chapel objects and like make it more easier for users to interoperate. But yeah, thank you.
Don't think we have time for questions right now, but since you're doing it.
Oh, we have a lot of time in the buff in 20 minutes.
Yeah.
For the questions.
And I'd like to introduce Alexander Plavin, who's been in the Julia community for a while, doing lots of stuff. So take it away.
Yeah, hi everyone. Indeed, I've been using Julia for quite some time, but this is my first in-person JuliaCon, so I'm happy to be here. So today I will be giving this kind of lightning talk about the part I really like in Julia is that you can just use built-in collections, arrays, as tables and get all the features with just built-in types, effectively. So, so there are really kind of two ways, two approaches to using tables and tabular data manipulation in Julia. One is the way that is most common, like the only way in Python and R, and I guess it's the most common in the world for that reason, is to use custom container types, like data frames and memory data sets. Maybe I missed something. But also in Julia, you can just use generic collections like vectors or abstract vectors of, in the base case of named tuples. And I really mostly use tables in this matter, and this will be the focus on my talk. So in the context of this talk, kind of arrays as tables in Julia, there are kind of orthogonal choices. First of all, like what data structure you use, and there is a choice of like row-based, column-based, and kind of the either vectors or struct arrays, or maybe like some fancier data structures as well. And orthogonally to that, you can kind of choose from a wide variety of packages. And today I will highlight some like how tabular operations look in base Julia and what data manipulation.jl brings. But of course, the ecosystem of packages that work with arrays is huge in Julia. So one of the reasons why I like this using built-in collections as tables is that they and their operations give you the familiar Julian performance model. So if you call this types table, it's extremely fast. You can even use it in tight loops. If you don't care about performance, you can use type unstable code and so on. So this is like what you have everywhere in Julia. So nice fit for tables as well. Also, it's of course composable. You can like choose your types and your functions independently, and everything works together. So just kind of mostly with base Julia and some CSV reading packages. You can create a table, don't need any imports whatsoever. You can do so-called select, that is map, filtering, sorting, limiting, everything like this is already built into Julia. You don't even need any packages. So what is data manipulation then? So it is kind of inspired by split imply combine.jl. That package was pretty popular at some point. I contributed to it about 2 years ago. It's not really actively developed, and some things can be done cleaner and or more composably or modular way. So data manipulation is kind of, in my opinion, improving on that and getting more features in a kind of more consistent interface as well. So it has kind of two key parts to it. First is more convenient and simpler piping syntax that is for like everywhere in data manipulation. That is in datapipes.jl. I have a poster later today in the poster session. And also orthogonal to the syntax part, there is this functionality that is commonly used and commonly needed for tabular manipulation, but is not present in base Julia, like grouping, joining, some advanced maps, and so on. So this is just a glimpse of the poster. It will be in the poster session today on data pipes. And now let's move to, and just quick overview. Of course, I won't give you like a whole kind of complete description of everything that's available. Basically, like it has both traditionally tabular operations that work generally how you expect. They get kind of any collection in. It doesn't even have to be a table. It can be a collection of arbitrary objects. You can do grouping, joining. Joining is in flexi joins that I will also be giving a dedicated talk tomorrow. So this is one part. So kind of more general tabular operations that work with a wide variety of types. And the second part is kind of mostly small extensions to base functions that are also naturally occurring in many data manipulation workflows. So actually, I don't know if this is the bottom of the slides are visible. So it has, I think, to my knowledge, the most feature-rich lazy map in Julia. There is skip that is like skip missing, exactly like skip missing, but more general. You can like skip names or whatever. There are some things like to work with nested data. Like you have this name tuple. Imagine it's your table row, and you can nest it. Everything is also like everything there is performant, compiled, like type stable and everything. So as I won't be giving a kind of like full description of what is available, I will just say a few words on the design principles. So I really, in the design of data manipulation .gl functions, I follow the example of base Julia because I like how it works with building collections. So the functions, they take arbitrary collections, not just vector of named tuples. It can be your like favorite abstract array of your favorite structs. It can even be a tuple. This is can be convenient in tight loops if you have a lot of small tables or you have like a single small table and you want to run like optimizer many times. If you have like 10, 20 rows, it can be faster to just have a tuple. There is a heavy use of lambda functions for flexibility. Instead of specifying like a column name, you can provide arbitrary function. Same as you have in base and map. It takes a function in the collection or a table. Same approach is, for example, in group. And as I said, the familiar performance model, write type stable code for performance, it will be fast everywhere, or write type unstable lambdas if you don't care much about performance, if your data set are smaller. Of course, there's always this caveat. Type stability is not 100% obvious in Julia. There are often these like Slack threads or discourse threads discussing it. But this is kind of, again, what you get everywhere in Julia. To sum up, really kind of in Julia, what I like with working with like tabular and quasi-tabular data, that a lot of operations are possible, convenient, without any custom types. Like in Python, you cannot really do that with built-in lists or NumPy arrays. No, it's not very convenient. Base is already enough for many basic table transformation. Data manipulation.gl is a package that provides even more tools for that. And the key thing here is that you write your code using some functions. And they work on row-based, column-based arrays you can choose afterwards. They work on tuples for small tables. And actually, most of the code is compatible with SQL, with MySQL collection.gl package. You can use map filter and group that will work exactly the same on SQL tables without materializing everything, and as it works on in-memory datasets. So yeah, that's it from my side. Thank you for your attention.
Yeah, I think we probably have time for a quick one question. And next speaker, please come to the front for the setup. Any questions?
So with data frames, as I understand it, those are actually abstractly typed on purpose. Can you talk about like maybe some of the trade-offs there between having something like concretely typed and like what you lose when you're going towards that?
What you lose when you go into abstract type corrections like data frames is that you lose this kind of like familiar performance model. So first of all, they work. I mean, they are heavily focused on flat tables. If you want like kind of some nested structs, it is kind of a whole kind of worms how to work with it. They have to be careful like not to just pass lambdas, but like pass more. They take more structure kind of inputs. And also, if you have data frame syntax, it only works with data frames. If you have basic collection syntax, you can choose whatever type you want. Yeah. But it's kind of course a huge topic.
Yeah. Thank you, Alexander. And I'm happy to introduce Lilith Hafner, who's well known among the people who are trying to make sure that Julia keeps moving forward in the triage group, like really keeps that going. So take it away.
Okay, let's see. Okay, autoloads, basic autoloads.jl. When I type this in the REPL, run that for me. That's just the kind of the gist of it. It's a very simple package. If you're thinking during this talk, wow, that's trivial. You're right, it is trivial. Cool. So outline of this talk. First, I'm going to motivate the package with a demo, then talk about the API of the package. get audience input on future API development, and have time for questions. So motivation, why we want this. It's for tooling. It's if I want something to always load, always be available for me, and I want it to just work. So use the tooling without loading the tooling. I don't want to type using chair marks. I don't want to type using jet. I don't want to type use, like, if I'm using the constructs from the package, I want the package. And I want it to be minimally invasive. I do not want to load jet in my startup file. That feels like a very bad idea. And I don't want unnecessary pre-compilation either. And should be low memory overhead. Loading packages slightly increases that, or significantly depending on the package. And I want it to be reproducible. My environment, I don't want to have a bug that I come into and I post it on GitHub and someone's like, whoa, I don't see that bug. So that's part of minimally invasive. So now for a demo, if I launch Julia, this is just normal Julia. I have a very small startup file. If I look at my loaded modules, this is a list of all the modules loaded on the system. Notably, chairmarks is not loaded. And then if I use a construct from chairmarks, like benchmarking, sorting, it works. That's cool. It automatically loaded. Wow, who would have guessed? Everyone looks so surprised in the audience. That's a joke, nobody's surprised. Great. And if we look at loaded modules now, we can see chairmarks is loaded. That's the gist of it. Oh gosh, I'm just gonna, okay. And what if it's, so let's look at my startup file. This is from pagers.jl or something, from terminalpagers.jl, which I don't have, but a package is available, so I'll install that. And now I'm gonna precompile live during a lightning talk. This is a risky decision. Great, and that's, okay, maybe I need to, okay, well, I'm just gonna open my startup file here because I couldn't figure it out in, where's .julia? Oh gosh. I'm on my oh, I need to expand the home directory. Thank you, thank you. Ah, yes, 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 yes. Thank you. Pager takes a string as input. Great, that's my startup file. Thank you for the help from the audience for figuring this out. And what this does is register autoloads. If I'm in an interactive session, then it'll import basic autoloads and register autoloads. And what an autoload looks like is a series of strings and then an executable to run, or an expression to run. And I left it very general because if I had lists of packages on the right-hand side, then people would open issues being like, how do I run an arbitrary expression? Whereas if I just have arbitrary expressions only, nobody's going to open an issue saying, how do I call using? Works for macros, works for functions. Great. So that's the demo. So some edge cases. How literal is when I type this? The line I drew is if it appears as a symbol in the AST, then you typed it. So if you trigger on @B and someone types @benchmark, that does not trigger. It has to be an exact match. But if you say x equals 5 and you have an autoload triggering on x, then that will trigger. Another question is how invasive should the auto install prompt be? I hacked in that auto install prompt. Do we want that to always happen if someone types using, or just if it's at the top level like it is in the REPL? And should there, right now it only executes something on that right-hand side once up to uniqueness of expression. Do we want to do that? Should it do other checks? Like, does it only run if the module isn't loaded or something like that? Basically, how complex should it be? And this is something I'm open to feedback on. Yeah, I'm also open to help getting code coverage up. It's hard to test this. I don't know how to test an interactive thing like this. Yeah, and I'm open to questions or comments or feature requests. Yes?
let's say you use a macro to parse a string into the AST, and then that would be one of the triggers. Would that still trigger this?
A macro to parse an AST into the string.
A string into the AST, I guess. Like as an expression.
Like at eval.
Yeah.
Symbol at test. Something like this.
Yeah.
Like.
Yeah.
We're talking this?
Something like that. I also can't remember it off the top of my head.
I don't know. But that's not in my target use case. So if that fails, whatever, I don't care.
Yeah, Haley is great package. I remember I asked you a few questions on GitHub. So I wonder how up to discussions that we always trigger on like symbols that appear, or there is a chance that we can reconsider it to only trigger when the symbol is actually used. So if you want to like auto trigger on min, it won't trigger when you have like min equals 5.
Mm-hmm. Yes. So there's trade-offs here. Yeah. The more complicated the API, the harder it is to maintain and the harder it is to learn. And I have yet to see an example of this like actually posing a problem. Like people aren't triggering on min, and people aren't setting at test to mean something else. So I haven't seen a practical issue, and I'm hesitant to add a feature unless there is an actual, like a practical issue. So I'm with you, I hear that theoretical issue, and I'm like, I'm not convinced by a theoretical issue that warrants.
Yeah, I just don't want to like manually load using statistics. I just want it like to be available whenever I do like mad or mean or whatever.
Yeah. And so you might set mean. Yeah, that seems plausible. And you can do that with, on the right-hand side, you've got arbitrary expressions. Oh, wow, audio. So you can use an arbitrary expression on the right-hand side to get what you're looking for there. And then the cost of that is because of the non-invasive auto-install prompt, you'll have to have statistics installed, which if you're regularly doing that, that's probably fine. Also, that's a standard library, I think.
Yeah, we can talk through.
Any other questions, comments? Yes, please.
For testing, I was thinking about some work I did a long time ago in libgit 2, where there's like challenge prompts where there's user feedback required, and then you kind of write to standard in. So there may be some inspiration you can take from tests and base for there.
Yeah, cool. Thanks for the advice.
Yeah, last thanks, speaker.
Thank you so much, Lilith. Good to see you again. And now we have Luca Ferranti again for a long session. I guess once he gets set up, get to learn more about Chapel and Julia interoperability. Cool.
Chapel and Julia are the things.
They love each other, right?
Yeah.
Oh, and we also have Michael Ferguson. Is it from HP? Oh, nice.
Yeah, so hello everyone, and welcome to this to the first and hopefully not last Julia Chapel crossover, the best crossover ever since Arrow and Flash. So the structure is roughly the following. So I'll give a very short introduction, like why I got into Chapel, like what I like. Then I'll hand over to our rockstar Michael, who is a core developer of the Chapel language at HP. He will give a short, better introduction to the language. And then we have a very informal, cozy discussion. We can chat about whatever we want. This Hack'em is public, so the link is, I can write on the board maybe if there's a pen. Michael has also a QR code, easier. And so you can write questions there, and we can take it wherever we want. And we can chat. You can write questions, vote questions, and interact. Yeah. So, yeah, so I mentioned briefly in the talk like how I got started with Chapel. Like I was bored and I came across the language, and I thought it was cool. And like mainly two things like really struck to me. First, that the community was very cozy, like Julia. So coming from Julia community, I had already very high standards of what I expect from an open source community, and Chapel fulfilled that. So great. And also, like one thing that I found very cool, which I don't see mentioned in a lot of places, is that coming from Julia, I noticed like my mental model of Julia was helping me understanding Chapel a lot. So a lot of things typical in Julia were actually translating also to Chapel. So it was like a match made in heaven. It was very smooth transition. Maybe I can give a very short example of one of the many features. I don't know if you can read, but like, for example, one of my favorite features like this where clause, which I think they're very similar to like Julia, where clauses, but in a way more powerful, like more similar to what computed_fields.gl does. So basically here I was implementing some prototype of interval arithmetic, and basically I want to do like generic operations like interval with real numbers, interval with float, and so on. And now basically I can see that this is like minus operation on A and B, where either A is an interval or B is an interval. So I can define like in one line for all mixed cases like interval, interval, interval real interval, and so on. So pretty cool, pretty expressive, so similar to where clauses. So one thing that I don't see mentioned in a lot of places that I think like Chapel, if you are really interested into like generic programming or like this very fancy generic programming, has a lot of features, pretty interesting. And coming from Julia, it's very easy to grasp these features. It's a small syntactic feature, but something that I thought was very cool. Yeah, and without boring you anymore, I'll give it to Michael, and he can give a better overview of the language.
All right. Well, thank you all for coming. I will, whoa, I don't know how I got to that part already. Let me try pressing that button. Okay, yeah, I'll tell you a little bit about Chapel, and I'll show a QR code. Like Luca said, we'll talk about basically whatever it is you want to talk about here, but I'm going to spend a few minutes talking at you, and then we'll discuss. So I'm a software engineer at Hewlett-Packard Enterprise. I first started working on Chapel in 2009. So I've been involved in the project for a long time. I've worked on language design, compiler implementation, including communication optimization in the compiler, working on the standard library, including sorting. I'm a huge sorting nerd, and some applications. So what is the Chapel programming language? It's a language designed for productive parallel programming, particularly on large-scale systems. It's easy to use. Here's a story from one of our users who's in an academic group at Polytechnic Montreal. His group does aerodynamic simulation to do aircraft wing design. When his group switched from other tools, including, I believe, C and OpenMP to Chapel, they saw a big productivity boost. He says they ask students at the master's degree to do stuff that would take 2 years, and they do it in 3 months. Chapel's portable, runs on a variety of HPE systems, other supercomputers and clusters, also a Mac or a Unix system. It has GPU support for NVIDIA and AMD GPUs. It's fast and scalable. One of our results is we've achieved about 8.5 terabytes a second when sorting hundreds of terabytes on a Cray EX on 8,000 nodes. And that code that was doing that was 100 lines of Chapel. It's GPU ready. We have users who are writing applications that run on GPUs. We've run some of those GPU applications on Frontier and Perlmutter. And it's open source. It's Apache 2 licensed. And we're in the process of joining the High Performance Software Foundation, which is an umbrella group within the Linux Foundation. And then our website there is chapellang.org. I'll have a QR code later if you want that. So here at JuliaCon, what strikes me is that Chapel and Julia have a lot of overlap in that we both really care about performance and productivity. And I think not everybody does, or at least not to the same degree. And I'll say that in a little more concrete way by referring to this chart that Luca showed a minute ago. That we have these are from programs from the Computer Programming Languages Benchmarks Game website, where people can contribute implementations. And then we have, with each square, we have the geometric mean of the smallest implementation of a benchmark in a given language. And with each circle, we have the geometric mean of the fastest implementations across all the benchmarks. So that's how we draw a single dot for square for Chapel and a square for Julia. And across all the benchmarks, you can see that Chapel and Julia are in the lower left corner of the plot, which indicates smaller programs and faster programs, which is where we want to be. So we love performance and we love productivity. I've recently been doing a performance and productivity survey of distributed memory programming techniques. I compared Chapel, MPI, OpenSHMEM, and some others. This graph shows my results. This is very similar to the last graph we looked at. This axis is time, and then this axis is lines of code or complexity. So ideally, you're down here in the lower left, and that's where our Chapel versions are, and other implementations, they can compete, like this conveyors. One can compete in performance, but is quite a lot more code, and some of them aren't matching the performance or the size in terms of productivity. If you want to play with this, I'd love to see some Julia implementations to compare with. When I started looking at it, but I'm not very familiar with Julia, and I wasn't really sure which distributed Julia library I would want to use, and thought, oh, well, maybe my MPI part already covered it. So anyway, if you're interested in that, I'd love to see some collaboration there, and I would be happy to include on the summaries. That same sort that I just talked about is actually this sort that I mentioned earlier that's part of Arcuda. Arcuda is a data exploratory data analysis framework written in Chapel that you can use from Python. And this is a scaling result from that sort where we got to terabytes a second of sorting on 8,000 nodes. And again, that was 1,000 lines of Chapel code. Here are some other benchmarks. In the background, I have sort of implementations in C or MPI or other more traditional things. And in the foreground, some Chapel implementations. And this is a complete program on the top. On the bottom, there's a little bit hidden, but it's not a lot. It's about how do you create the update sequence. And then these are performing competitively between Chapel and these reference implementations in these cases. And then here's another similar example along the same lines. So I thought you might be interested to see some details of like, well, when we get to writing a function or something, how does Chapel compare to Julia? So like in Julia, you might write this. I wrote a really stupid function that just adds 1 to a number, but I didn't put a type on it, so it's kind of a generic function, or maybe it's runtime typed, I don't know. But in Chapel, you can write something conceptually very similar. Chapel is an ahead-of-time compiled language, so we consider that a generic function that we're instantiating according to how you call it. And then, in Julia, you can just create variables as you use them by assigning them. In Chapel, you need to declare them, which is pretty normal for compiled languages. There's sort of the age-old debate of if you spell it print line or write line. Ranges in Julia, you have the colon separating them. In Chapel, we use dot dot, but they mean the same thing otherwise. We have the same array literal syntax, but over here I showed declaring an array variable because I wanted to show the array type. I actually forgot to put in there, sorry. But the point I wanted to make here is that the array, when you declare it in Chapel, you tell it what the bounds are, including the start bound. So you can make 1-based arrays or 0-based arrays or negative 300-based arrays or whatever you're into. Obviously in Julia, the normal arrays are 1-based. In Chapel, our tuples and our strings are 0-based. So it's sort of a mix. Julia has garbage collection. Chapel has a more scope-based memory management idea where, for the most part, things get freed when they go out of scope. And in more complicated cases, you can use borrows and shared things like similar to Rust or C++ features. And then here I've got some details on the parallelism and distributed memory programming. So in Julia, if I want to run something multi-core, I might write a loop with at threads and 4, or at least I'm not an expert. That's what I understand from being here all week, right? So maybe I want to use a different threading framework, but that's the general idea. In Chapel, we write for all. For all is a keyword. It's part of the language. It does something very specific. So in Julia, we have these different libraries defining macros that can support this way of running a loop in parallel. In Chapel, we have the library defining a parallel iterator, but the language has defined what does it mean to write for all, and that means calling a parallel iterator. And then within a parallel iterator, you can say, oh, I need to make this many tasks, or I need to run it on the GPU, or whatever it is. And the other thing I wanted to mention here is that from some of the earlier talks, I heard that Julia, when you're writing this kind of code, you might accidentally write a race condition where you like try to accumulate in a stupid way, where you just add to an outer variable. In Chapel, that thing, at least for the simple cases, you'll get a compilation error because of the way the language is defined, where you're not allowed to modify something like that inside of the parallel region as something like an integer. And oh yeah.
For all is the standard for loop, or it's only for the parallel?
That's the parallel. The serial loop is just for. And then here we have sort of another similar feature between Chapel and Julia, which is what you'd call broadcast and we call promotion. Broadcast, you don't, in this case, maybe you don't need to put the period because it would call a function. The plus on vectors might do this thing anyway. In Chapel, we'd call it promotion, and in our case, it's always parallel. And then when it comes to distributed computing, I'm not the expert on it, but I'm understanding that people like to use MPI.jl for running on like a cluster or supercomputer, and that's going to involve send and receive and collectives, just like all the other MPIs. Chapel has a different model where implicit communication is built into the language, so you can access a variable that's declared somewhere else, and it will just do communication to get the value. That's implemented with one-sided put and get and active messages that are supported in the network, and we access that through libfabrics or GasNet. Yeah.
So does promotion happen with arbitrary functions, and does that require special syntax, or how do you differentiate between maybe two functions where maybe two methods where maybe you sometimes want to run a parallel and sometimes it might make sense not to?
Right. So we have other ways of controlling the parallelism. So if you just you don't want it to be parallel, then there's another keyword for that. But the way it works is that if you have a function that takes in like an integer or a floating point or two of them, that's sort of a scalar thing, and you're giving it an array that's of the same type, then it will do the promotion.
there's like another method with the same function name that can take.
Yeah, then if you had another overload that took in an array or took in it was generic and it took in anything at all, then it wouldn't do the promotion. It's sort of like the promotion is only, if you only gave me, you know, f of integer and integer, right, then it'll do the promotion. But if you gave me f of integer and integer and then f of anything and anything, then it would call the anything version with your arrays.
Okay, so there'd be, is there a way to like then say, actually I want the promoted version here, or no?
I don't like it. We don't really think about it in the same way as Julia, obviously, where like in Julia, it's like a variant on the operator, right? And I think that's cool, but that's just not how Chapel thinks about it.
Okay.
Okay, and then another, we're getting already into a great BOF territory. I don't think I need to, I think we should just do the questions. Yeah, go ahead.
If you define integer plus integer and do a plus b plus c, where a, b, and c are all arrays of integers, does that do broadcast fusion? Does that allocate intermediaries?
It does not allocate intermediaries, and the way that it does that, we would have different terminology from, I think even the way you think about it is probably different from how we think about it. The way that we think about it is that all along that was actually creating some kind of parallel iterator. And then, so if you like said D equals A plus B plus C, right? Then we sort of view the whole thing as some kind of parallel iteration that's going through in like a zippered manner all of those arrays.
Yeah, that makes sense. Nice.
So the next thing on distributed computing is, in Chapel, really important feature is distributed arrays, where block distribution is the main one that's working well. I know that Julia has some packages to do distributed arrays. What I don't know is how well they are going in practice. Do they perform well enough? Like, could you write that radix sort comparison in them and get a good performance or not? I don't know. But related to distributed arrays, what you can do in Chapel is with this parallel loop, because for all says, go ask that thing you're iterating over how to do it in parallel. If it's a distributed array, you get distributed iteration. So if I write this for all element in my distributed array, that will be a parallel loop running across the whole machine if I've got my array distributed across the whole machine. So as in like lots of nodes, lots of cores. Anyway, so that's kind of my little table. What I have next is a bunch of sort of stories about real users of Chapel. And we can, I'll talk about these a little bit, and then we'll go back into more Q&A kind of way. I already mentioned the aircraft simulation application. That's about 100,000 lines of Chapel. It runs on desktops and HPC systems. We have some users who make much smaller programs. For example, one user made some coral reef image analysis application that was just a few hundred lines of code, runs on desktops, HPC systems with GPUs. And then we have another user who's been writing a lot of code, like doing atmospheric data analysis, but he doesn't run on HPC systems at all. He just runs on a desktop and sometimes uses GPUs. So, and he loves it for that. So you don't have to use the distributed memory capabilities to find something to appreciate here. All of these users, we've posted interviews with them, so you can learn more about what they were doing. And I feel I'm boring you because someone walked out. Next part I have, yeah. It's like it's cosmic balance. Thank you for coming. I'll cover a little bit of like, just to wrap your head around like what is this programming language's model. I'll cover a little bit of some little examples, and then this sequence is all that I have left in my slides, and then we'll go to discussion. So here I've got a little cartoon of 2 nodes, and I've got different CPU cores in blue, and then I've got some different GPUs and notional GPU cores and GPU memory, right, on those nodes. And so the question is, okay, when I'm running my program, when is it going to use those different features? And that's what I'm going to be showing you. So here's an array declaration. That creates a local array. You'd do something else if you wanted to make a distributed array, but you can, as I said. And then you can use a for loop to go over your array, maybe add one to every element is what it's doing here. So that little gear is indicating that this is happening in one core on one node. If I put the for all keyword in there instead of for, then it'll be parallel across the cores on that node. So that's what those gears are indicating there. If I use the block distribution and create a block distributed array, now when I do that for all, it'll be parallel across the cores on both nodes. Going back to what we had a minute ago, we need to talk about sort of some terminology. In Chapel, we call, like on first approximation, a node is a locale. But it's a little more complicated than that because we have an idea that if you're using GPUs in particular, those GPUs are different from the CPUs. They have different memory, they have different execution environment. So we think of those as also locales. So here we think of, I've got a locale for node 0, and then it has sublocale for GPU 0 and GPU 1. And then in the language, you can say here to ask for something that tells you what the current locale is. There's an array for all the locales, and then you can get to the GPU sublocales with the .gpus. Okay, and then there's the on statement that says where to run something. It does not introduce parallelism, so this just does what I had before that was running on those cores, but now we're doing it on locale or node 1 instead of 0. I could put .gpus, and now we're doing it on .gpus at 0 on that GPU, do this thing, and now we're running it there. Here can say wherever you're running, and then go into the GPUs on that wherever you're running. Co for all is kind of like for all, except it makes a task for every iteration instead of blocking up the iteration space among tasks. And then you need that if you're doing something more manual. For the slide, it helped to go from curly braces to putting a do instead of to fit that on one line. So now I can say, create a task on each GPU and then do the following. So that's why this is running on each of those GPUs. I can create a task on each locale, and then on each of those locales, create a task on each GPU to get something on all the GPUs. And then if I say I have a distributed array or an array on locale 0 or something like that, and I want to compute on it, update some element of it, I can use array slices to move part of the data around, or I could access an individual element, which you can do, but maybe might not be the best for performance. I'm going to skip that. So here's some QR codes if you're interested in looking at our website or anything, although chapel-lang.org is probably easy enough to type in. And then here's the main QR code that you really should pay attention to right now to help us figure out what we're going to talk about, what we're going to talk about next. And then I would like to invite Luca to come back up, and we'll proceed with discussion and see what you want to talk about. Do you want to plug yours back in?
What?
Do you want to plug that back in to the?
No, maybe I can use just.
Not right now.
Because probably we're going to do some demos on the flies.
That would be fun.
Yeah.
I'm ready to do demos if you want, but you have to ask me.
Yeah. So we have HackMD. There was the QR code on the screen, and the link should be fairly typable. So now it's open discussion. Whatever you want to ask, discuss, we can ask, discuss. And here we listed a couple of topics already, like to avoid, empty HackMD. And if you want, you can vote the topics. Just put an X next to them in edit mode, and we can discuss of everything. Anyone has questions, comments?
Oh boy.
I think Danny was first.
Yeah. I don't know if
Honestly, I thought we hadn't recorded it, but yeah. Thank you. Yeah, so I was looking at the part where you have like basically like kind of Fortran like arbitrary indices for arrays type of thing. One of the issues that has come up in Julia is there's an offset array package that you could have arbitrary indices, and sometimes when one user defines something and another user uses that array and doesn't know that it has indices, you're getting the wrong elements. Have you seen anything like that, or do you have something that protects against that?
I think we have some similar issues, but it's not about the array start index. That one, it seems like the language has kind of absorbed it well enough that, well, I've got an array, it's got some domain is the terminology we use. That's the index set of the array, and there's some lowest one, but they're also multi-dimensional arrays. So I might have like a 4-dimensional array, and then I want to ask for when I ask for the shape of the array, it gives me ranges, right, for the start and end. So that makes it less likely to have a problem with the start. Obviously, you can still have that bug. What I've seen more is issues where our chapel ranges can be strided. I think Julia has that as well. And a lot of code is written so that it'll query the start and the end of the range and just ignore the possibility that it's strided. And that seems like a more, well, in my experience, that's a bug I've run into in practice, where I don't think I've seen everybody just assumes it starts at 0 just because it would be weird, right? I think it's a different setting in Julia where you have sort of normal arrays and then special arrays that might not start at 1, right?
Like the cultural thing helps probably.
Yeah. Yeah, and actually the full language used to be 1-based. And then at some point we said, well, Python's 0-based, so we're going to confuse everybody. But so if you look closely, the syntax we have for ranges actually makes more sense if it's 1-based. At least that's my opinion. But for arrays, it's configurable. You had a question.
Yeah,
Here comes the mic.
Sorry, I missed the first part. I just moved my car. So did you already go over the Chapel Julia integration or interoperability and different approaches or different use cases for that?
Right. So Luca talked about that demonstrated that in an earlier talk. Mm-hmm. And I think that some of the most exciting options there are maybe if Chapel can call Julia code, then Chapel users can have access to lots of great solvers and matrix libraries and stuff like that. And maybe if Julia can call Chapel code, then Julia users can have access to some distributed computing mechanisms that are hopefully easier to write than using MPI. Although, maybe, I don't know, maybe you'll figure it out, the perfect way to write distributed computing with some other Julia library, but.
No, well, that's what I want to do is the thought was use Chapel to do the distributed compute or the GPU compute, but I'm already committed to the Julia package world and or Julia hub. So would it even be possible to deploy this out onto hub or onto EC2 instances and that kind of stuff?
Well, I mean, Chapel can run on EC2 instances. We have done that, and you have some support for the elastic fabric adapters as the network. But it depends on what specifically you're trying to do and which features you're trying to mix between the languages. And what Luca showed was sort of like an early demonstration of hey, look, I can make it work to call code between Chapel and Julia, and you might want something rather more well constructed. But it just depends on how much you want to get out your wrench. Really, is what I'm trying to say.
Okay, that sounds great.
Real quick before we go on to that, relatedly, at HPE, right, we do support some of our Chapel users. So if you you know, with contracts. So if you run into something that you're like, I would love to do this, but I don't know how to do that. If I could do that, then I could go to here, and that would be great. Then it'd be a good time to reach out. Go ahead.
I'm seeing like a difference between Julia and Chapel, where Julia is single thread by default and Chapel is multi-threaded by default. Is
Absolutely.
that like
Yes.
Yeah, and so that explains the like difference in sorting runtime.
That's right.
Julia sorting was single threaded, Chapel
Yes.
sorting multi-threaded.
Yes.
And that is, I mean, it's cool. Yeah, checks out. If you have enough cores in your computer, it's faster on the micro benchmarks. How does that play out? Like when thinking about utilizing resources on a larger, maximally efficiently, it's like you want to do the distribution and at the highest level possible, and then the multi-threading at the highest level possible. So, if for example I have a big loop, and in there with 100 iterations, and then a bunch of work in each iteration, and for example one of the parts of that work in that iteration is sorting, will we go single threaded for those little things if we already maxed out parallelization?
Yes. So what we do in Chapel is what we're really good at is sort of that for all loop the data parallel story, right? We have other ways of creating tasks that I showed the co for all a little bit, but for the for all story, when one of those iterators, the parallel iterators that's implementing the for all based on whatever data type you're iterating over, one of the first things that they normally do is say, how many tasks should I create? And they do that by saying, well, how many tasks did you set up the Chapel run to be using, right, for data parallel loops? And how many tasks are running right now, right? And if there are too many tasks running right now, it just won't bother. It'll just say, that's fine, I'll just do it in one task. And that's how we handle nested parallelism. And that seems to have worked pretty well for us. And it seems like a kind of an easy way to address some of the things people were fretting about earlier in the threading, Julia threading talks. And we do that there's just an atomic per node that counts how many tasks are notionally running.
Yeah, thank you.
So what's the setup requirements for Chapel arrays JL? Anything? I mean, you have to have, obviously, like Chapel installed, that's nonsense.
Well, I mean, this doesn't exist. So the setup requirement is someone has to write it. Okay. But the prerequisite to someone writing it is having someone who cares about it. So.
Okay. How big is the Chapel setup for getting it installed and set up on the machine? Is it relatively small? Is it a big deal? During the first half of this talk. Oh, you did? Okay, yeah.
I'm glad. I wrote a blog post about comparing standard library sorts, and the Chapel version is faster because it's parallel, right? So it's sort of like completely unfair, but this is also kind of the point, right? Like I think that if people are writing applications where performance is the goal, the hardware is really parallel now. Like my phone has 8 cores or something. Like you can't find anything where if you're not doing like some kind of embedded thing that's not in some way parallel. So I think that's what we need in the world, is something that's sort of more set up for parallel by default. And for Chapel, along with that comes the sort of the culture of like everything in the standard library is supposed to work in parallel. Like maybe everything isn't perfect, but that's kind of a reasonable expectation for a Chapel users to go and say, hey, this is a parallel language I called sort and it ran in one thread, what gives, right? Whereas I think in Julia or Rust or Go or any of these things, right, that's not the expectation the community has created. But anyway, I was really impressed with Julia's sorter for single thread, right? It was really good for that. Yeah, there you go. Good work.
Maybe I'll make it parallel in the hackathon. So the trouble is, like, I don't. First of all, Julia, like, you just type Julia, you get one compute thread. You get a
Yeah.
thread, you get a GC thread, you get a compute thread. And then there's this design philosophy. Talking about why Julia's sorting is single thread by default. If you mentioned that, like, if you were a Chapel user and you call sort and you're like, oh, it ran in one thread, what gives? With Julia users, if someone's like, oh, I ran sort with my custom by ordering, my operator or my custom comparator, and there was a race, like, what? So there's a different expectation.
Right.
The Julia user has the expectation that they can provide a non-thread safe comparison function and it'll be fine. And the Chapel user has an expectation that sorting will run in multiple threads. So it's like, it's tricky. With Julia sorting, we could say if you're using default integers and default sorting, like if we're using combinations of things from base that are known to be thread safe, or if you explicitly opt into multi-threading, then we could do it multi-threaded. But it's an infrastructure problem. And so the utility there in the Julia context of adding multi-threaded sorting methods to base is a lot weaker. And I think that explains why Chapel sort is multi-thread and Julia sort is single thread. And it's, yeah, I really hear that cultural thing. Because with the cultural expectation of the algorithms will be multi-threaded comes the cultural expectation that the algorithms will be thread safe for if they're used within a thread and there's multiple
Right.
things
If you
going
can
on.
provide a function to them, that you have to make it thread safe too.
Yeah.
That's right. And I mean, it applies just as well to something like Python, right? Like Python's standard library sort could go and spin up, 128 cores on my AMD server, right? It won't, because that would confuse everybody, right? But it could. Like, there's nothing about the programming model that's like, it makes that impossible. It's more, as we said, it's more of a cultural thing.
Just another question related to sorting. Like, can you provide a custom sorting function in?
Yes.
How do you deal with safety, thread safety?
I just expect that the users know that it needs to be callable from
there
lots of threads. Yeah, seriously, it already covered. One of the things that I'm excited about in Chapel's standard library sort that I haven't seen in any other standard library is that we have a radix sorter that can. I know, but our radix sorter, you can give a function. You can kind of give it the criterion to compare by as give me a part of the key at a time. And like in Python, and I'm pretty sure in Julia, right? You can take your complicated structure and say, here's the key that I'm sorting by. But maybe you wanted to sort variable length strings because you like suffix arrays like me, right? And then you can't, right? Because you don't know how long the key is, and it's unreasonable to return the whole thing. So anyway, that's one of the like I said, I'm a sorting nerd, so that's one of the things I think is exciting. And I don't know why every standard library I think should have in addition to the like A less than B kind of interface for sorting, there should be a give me key element I for radix sorting. It's my personal opinion.
I have a quick opinion that I think in the future in Julia, it'd be good to have maybe a dedicated function to say like, like this is, I want to sort this, but I know I'm passing something that is thread safe. Like, because I think we have a couple types of iterating, like different kinds of mapping and reducing that, you know, kind of have different guarantees on them for different performance reasons. And yeah, I think it would be a good idea to have that in Julia too, because I think when I use Julia, I often just assume, like, if I'm working in multiple threads, like by default, I'm making sure everything is thread safe already. Yeah.
Yeah, I mean, a related idea, I don't know if this makes sense for Julia because I'm not an expert there, is to find a way to mark the function that you're giving as how to compare as thread safe, and then expect that to kind of follow through.
Something. Something I was talking to Luca about at or lunch was, is there a way that we could somehow parse Chapel in a way to discover functions that we could then automate the building of Julia bindings for, or vice versa?
I'm sure that we can make tools to make the sort of interoperability easier. Chapel has some tools to make interoperability with Python easier in both directions. We have totally different approaches, actually, because of history. So we have ability to call Python code one way, and we have ability for Python to call Chapel code a different way. As far as the tooling you're talking about, one of the things that I had been involved in, you know, until I kind of got pulled over to different things, is an effort to revamp the Chapel compiler, which involves making it into a library. So you can use this compiler library to parse and type resolve, although the type resolver is not used in production yet. But when you have all of that capability, right, you can parse, you can get AST, you can resolve things, you should be able to ask questions like, is this an export thing? Was it taking in an array? Okay, if so, then I need to make this kind of wrapper for Julia, right?
Yeah, I think automating that would be amazing. Right now, there's a library, a Julia library called clang.jl, which uses C bindings for LLVM. And so we use that to parse C headers, and from the C headers, then we can automate the writing of C calls for C libraries. And on the C++ interop side, I think there's another library that writes some C++ code in order to automate the export of C functions as entry points for Julia packages. And so having both done that kind of approach and done it manually, I think it always seems to be more maintainable to automate as much as possible. And so it would be great if there were kind of at least a C interface into maybe the compiler in order to discover public functions and whatnot.
Yeah, those functions for the compiler library are C++, but I don't think they're like deeply C++, you know, so wrapping them is not out of the question.
I have a question about the infrastructure and like what is and isn't a standard library. I'm going to start with a little bit of context on Julia. Julia has base, which is always loaded, and Julia has functions in base like sort and types in base like int. Mm-hmm. And this notion of type piracy, so if a different package is really not supposed to define what sort does when given a vector of integers, that belongs to base. And so then it's base's responsibility to define the one and only default sorting algorithm for integers, which it turns out is like, you could have as big of an algorithm as you want for that, and it can keep getting better. And similarly, there's just like so much surface area on this sort function, and it all lives in base, which is really horrible because we should not be packaging this type of advanced optimization with base because not every user wants it. And I'm curious if Chapel runs into the same issue is with that, like, Yeah, if Chapel has that same issue with sorting and where the sorting code lives.
I mean, I think so. Like I think that the issue you're describing really comes from being a language with sort of more of a batteries included philosophy. Like if you were Rust, right, you'd just be like, whatever, that's in the, we wouldn't put that in the standard library. A standard library is like bit shift and plus, right? So, so you wouldn't have this problem because all the people who were trying to use sort would have had to say, I want to use sort, right? And so in Chapel, like when I've modified the standard library sort, sometimes I've made all compiles slower, right? Which is just annoying, right? But we have the same issue, and my view on it is that it comes with being sort of batteries included. And the way that we've tried to address it is mostly have the compiler drop things that are unused as soon as possible. So like, although it does parse that code, if you didn't use sort, it will just forget about resolving it or doing some of the later steps. Certainly won't generate any code for it.
Yeah, okay. I was hoping you might have a clever solution that allows us to do something other than keep it in base or remove sort from base.
Yeah.
Okay.
Yeah, that one's tricky, and it's. I think in our case, we don't actually include sort by default in terms of the namespace, but it is compiled by default, right? So.
Thanks.
More questions? Comments?
One of you should ask me to demo something.
Yeah. That's what I was going to say. Could you demo something? And one of the things I was thinking was, what do you do when you run into a situation where you're trying to write code and you don't know what the hardware resources are? Can you make the code flexible, or does it just naturally do it if you say, do this across all my GPUs, and you go like, oh, I didn't install GPUs on this thing?
Right. So with the GPUs, each locale has basically an array of GPUs, and if you had no GPUs, the array would have length 0. So if you said do the thing on all the GPUs, it would just be like, well, okay, I did a loop of 0 iterations, so I'm done. That might not be what you want if you put all your code in that loop.
That was my point.
Right, but
then you can also detect, right? And you can go, how many GPUs do I have, right? And it'll say like, oh, you have 6.
Yes.
And then you go, okay, great. So I'm going to do this on the first 3, and I'm going to do this other thing on the next 3, or I'm going to just say for each GPU, do all this math for me.
Yes, and we have an older GPU library before we got native GPU support that was really focused on like how to do a combination of CPU and GPU computation.
Okay, so then if I split my array into chunks to do work on different pieces, then can I reassemble it again after it does the work on all the different GPUs?
Maybe I'll try and demo something, but it won't be on GPUs because this machine doesn't have any GPUs. So.
Sure. But that concept works, right? I mean, isn't that part of what the deal is you can break things up, separate it out, and then bring it back together when it's done?
Yes. I want to grab a... let's see if I can... I just forget how to write this particular line. So, okay. So, distributed array. So one of the fun things we have in Chapel is called config const. So I'll declare that I'm going to make 100. Here, we'll make it 1,000,000. So I've got 1,000,000 there, and then I'm going to make an array, and it's going to be, this thing is our range way of saying up to but not including n. So if you were going to start from 0, that's probably how you want to write it. So there I made a distributed array. So now I can say, so this thing with zip, what I'm zippering together is the index set of the distributed array and the distributed array. And I'm just going to do the stupid thing and set the element to I. And then maybe we want to, after we do that, maybe we want to add them all together. right, as a way of figuring out, you know, some way of getting data out of our array in the end. So I've got a sum. These are all integers, so this is gonna have its type inferred to be an integer. I didn't give it a type. Just like this thing, this variable is its type. Oh, I made that constant. That won't work. Its type inferred to be a distributed array. And then you in Chapel you would use a well, I'll do it the easy way first. So plus reduce distributed array. Right line sum. So this thing is a standalone reduction. So I go over the distributed array. I could also write a little iteration expression in here to reduce over. That looks weird, but I could write something like that, right? And maybe, right? So now I'm summing up the squares of all of the, and put parentheses around that. So I'm going to try and compile that and see what happens. We'll see. You can grade me on my skills. So I've compiled it. It's you know chugging. This machine at HPE I'm playing with has a lot of nodes, but no GPUs. So I'll run it on 4 nodes. Oh, oops. So you know you have to wait for the queues and whatnot. Or maybe I did something stupid and it has an infinite loop. It would also help if I compile it with fast. If I want it to go faster, because when you compile like this, you get extra checks. If you want it to go faster and not have extra checks that slow your program down, you have to use --fast. Yeah, we're not winning the compile time race yet. Maybe later. That's the reason we've been like trying to really revamp the compiler, because it has a bunch of design elements that are really about performance, right? But not about good compile time. So I can run it again. And anyway, so we made a distributed array on 4 nodes and then added up the squares of the things. Just for fun, I will do a stupid thing in my program. And if it wasn't obvious, this thing tells it, please run on 4 nodes. So ideally, the Chapel has a component that interacts with the launcher, the job manager, job scheduler on the HPC system, and then that says go launch 4 jobs. You had a question?
Yeah, sir. I guess what the fast option is.
What does it do? It turns on additional optimizations and it turns off a bunch of checking. So an important example is array bounds checking. It turns off array bounds checking. So if you're debugging your program, you probably should leave it without fast while you're debugging, and then when you're done and you think your program is correct, then you can turn it on and see how fast you can go.
Is it like a fast math? Like the optimization that
Huh?
The optimizations that enables is like fast math?
Does it use fast
No.
math? Yeah.
We have a different flag for controlling floating point optimizations, so it does not turn on fast math.
Okay. And so is that option mainly used to accelerate execution, or?
Yes.
Okay. Is there different compilation modes as well? For like quick compilation versus kind of.
Some of the bigger projects using Chapel, for example, Arcuda, the data science framework, has something they call Arcuda Quick Compile that like turns off half of the libraries in order to compile faster. So that's the kind of thing that people are doing, but there's not like a flag to make the compiler just suddenly go 10 times faster. That would be nice, but if we had that, we would make it the default and then throw away the old thing.
4 minutes left.
Okay, I was just going to do a really stupid thing in here, and remember I had my reduction. I was just going to modify my variable from the distributed for all loop and try to add to it. And the other thing I'm going to do is I'm going to put all this in a function, because my story might not work if I don't. So I'm going to put it all in main. Okay, so now I'm going to compile that. You know, I really should have made this window bigger. You all are too nice to me. You didn't say anything.
So does this compile down to exe or bytecode or?
It can generate C or LLVM code. Right. So in here I got this error that maybe might not make sense if you have no idea what the terminology means. But what it's saying is that this variable, when we entered this for all loop, the compiler created what it called a shadow variable, which is a copy of it that is immutable because it's just an integer. So why would you, if you were just modifying it straight out of hand, you're writing a race condition, so don't do that. So that's how this case is ruled out. All right. Is there a question?
I guess that is thank you very much for presentation on chat. Oh.
Oh.
How has GPU, like what GPUs are supported, and what was the process you guys had in order to be able to support them all?
We support AMD and NVIDIA GPUs. We generate GPU code through LLVM. In principle, we could support other GPUs that had LLVM support, but we would need to know how to kind of do the runtime, GPU runtime calls to like launch kernels and move data around and stuff. And right now that runtime code is sort of the limiting factor. So if you're like, I really want it to work on Macs, right? And you're like, I'm going to do that. That's the code that you'd probably be mostly editing. All right, thank you, everybody. Oh, and before you go, I have little cookies for you, but don't eat them.
So who'd you pay to write this?
Write what?
You wrote this, right? The compiler?
I mean,
you wrote the language and the whole thing.
Not only me.
Okay.
I've been involved in it. Help yourself.
So how many years was this before you had something working?
Oh, that's a good question. I think that we had something usable to a reasonable person in around 2020, and the project started probably around 2006.
Wow. Okay, I don't feel so bad. Okay, so I tell my boss that. Hey man, so you've only given me 2 years. You gotta listen to what these other guys
Well,
say.
you know,
They're taking a long
are you making a compiler?
Well, making a code generator and runner. I mean, I like to pretend it's some form of compiler, but I'm not that savvy. I mean, Lexer, parser, and all that kind of stuff. Yeah. So it's quasi, I guess. I mean, you don't do the same thing to make a compiler, right? You can have your own Lexer and a parser.
Absolutely.
And then your parser generates out the endpoint, and then what is your parser generating this out? In this case, it just generates C.
We usually only
Because I like the ease of which you can go back and forth between GPUs and stuff.
Did you get a cookie? They're non-edible cookies. I'll leave a couple of them.
Can I take a look? Yeah.
Sure.
Leon.
So you guys got next? Anything? I saw you guys.
There's your problem.
Australia. Wow. Okay.
That should have solved it.
changed his res afterwards, right?
It's the active signal node that's giving you problems.
Yeah.
So it's just upscaling and downscaling to 1920 by 1080. Normally when you go into there, that's where you make the adjustment. Let's try this.
Hope you're enjoying the experience. Are there any people in your group in going Australia using Julia?
Not my group. I think there may be some groups. I just do it in my spare time.
Okay.
Pull it out, put it back in again, see what happens.
Because it's not even seeing an external display right now. It's giving me two problems.
I bought this laptop specifically because the other laptops.
Okay. Can you make sure you see it back there, please?
Something up.
Okay, I think that's working. Yeah.
Yeah, we just got to make sure we're seeing it on the stream first. Good. Okay.
Okay, I would like to introduce Alexander Leong from Boeing about efficient constrained optimization. Thank you.
All right, thank you. Yes, so today we're going to talk about a type of mathematical optimization, constraint optimization. So just a brief recap on what constraint optimization is. We minimize some function f naught of x subject to some equality and inequality constraints given by fi of x less than or equal to bi. So this is the objective function, and these are the constraints. To solve these type of problems, typically they employ what are interior point methods. And solving nonlinear problems typically involve some finite difference scheme or automatic differentiation for computing gradients and Hessians. So conic solver is a conic optimization solver. The difference for this type of solver is similarly we have this what we call a cone quadratic program, and these functions are given by matrices and vectors. So the variables here are p, x. X is the variable that we're trying to solve for. C is what encodes the objective function. We've got G, and which are the inequality and equality the inequality constraints are given in G. A gives the equality constraints, and then we've got these other vectors H and B that go together with these constraints. This S is just an internal primordial variable that's used by the solver. So X is parameterized by this cone K, and there's various different types of cones defined in this package. So we've got the non-negative orthant, second order cone, and positive semi-definite cone. So the non-negative orthant typically used in linear programming. So by manipulation of these equations, you can construct a linear program and various other programs. Looking at the positive semi-definite cone, that is used for semi-definite programming, which we'll cover soon. So what makes cone programming interesting is the expressiveness of of conic optimization. So this diagram depicts the various subsets of optimization problems that you come across. So QP is basically, LP is a subset of QP, which is a subset of SOCP and SDP. And cone programming is basically a way to encode a lot of these different cone programs. Another interesting program here that we're going to look at is sum of squares programming. And that's interesting because that can reduce to semi-definite programming to what are called relaxations of the non-convex problem. What we're going to do is we're just going to assume that everything is convex because that's what's easy to solve, and you get a lot of benefits by solving convex problems. So this slide is basically just summarizing what I've described. So key message here is basically manipulating those matrices and vectors allows you to express these different problems. And conic solve is written purely in Julia. And I know there's a lot of different optimization solvers already written in Julia, but what makes conic solve slightly different is it employs this Nesterov-Todd scaling, and it focuses on what are called symmetric self-dual cones. And the reason for this is for applications that require high order accuracy and numerical stability. If you've worked with something like Sudumi or Mosaic, they employ similar type of methods for solving these problems. But as you may know, Sudumi is implemented in MATLAB and Mosaic is a proprietary solver. So I went and decided, okay, I think we need something open source in the mathematical optimization community, and hence this package. So the mathematics around these cones is using what's called Jordan algebra, and that allows you to construct these symmetric factorizations of the gradients and Hessians. And by doing this, you don't need to, it just means that you have to work with the different cone types. You are basically restricted to that, but you know, it's necessary in order to get those performance benefits that I've described. Yep, so I covered that one. So one way to understand what a solver is actually doing is having a geometric perspective of it. This blue line sort of shows you the path that the solver takes. So it's, you know, we start at some initialization point here, and then after many iterations of running this solver, you get closer and closer to the optimal solution. Obviously, the minima of this function, this is quadratic function, is at 0, 0. And these lines here are basically the half spaces that define the constraints that need to be satisfied. So we see that it starts off in some infeasible region, but as we minimize those residuals, we get closer and closer to something that's feasible and optimal. And that's what we expect here. The solver performance. So when you're using a solver, or any solver for that matter, you might get some console output that looks like this, tabular form. You've got, in this case, dual residuals, primal residuals, the centrality, complementary residuals. You got this duality gap, which is the difference between the primal objective and the dual objective. And you've got the primal objective reported here. So for these 3 columns, you want all of these to come down to 0, and that's what we sort of see here. And then this gap, we want to get to 0 as well. And by having all of these 0, we satisfy the optimality conditions, and that allows us to be confident that we are at an optimal point and one that is feasible. If you do not meet those certain tolerances, then sometimes the solver would report this status back, in this case, a dual infeasible flag. This one, also, these plots here show the path that the solver take in terms of the residuals over iterations, and we see that polynomial convergence to 0, which is great. Let's take a look at some applications of how we use conic solve. One is maximum flow minimum cut, which is can be formulated as an LP problem. And we've got this graph here that sort of illustrates what we're trying to optimize. So these numbers show the maximum flow and minimum flow that need, that are constraints on this graph here between the nodes. And we can encode this in a matrix G. So the rows and columns give the weighted edges in this graph. On the right here, we can see the code that is required to define this optimization problem. In this case, instead of defining those matrices explicitly, what I've done is written functions to construct those matrices. So that reduces some of the tediousness in defining those optimization problems. Okay, so here's a technique that I use to convert those functions that encode the problem into matrix form. And an example of this in maximum flow is the flow conservation constraints. So flow conservation means the sum of flows into a node equal the sum of flows out of a node. And here, what we're trying to solve for are the flows given by x, and this can be vectorized via one example is this scheme here. So the technique is basically figure out what x represents, and then the equations would define themselves. Okay, so with the max flow min cut example, once we've defined those matrices and vectors, then we can write some function here to give us the objective, and then what we do is we pass it into the solver. So here we construct the problem, we give it the parameters and the cones. So the cones with respect to the variable x, and for because this is an LP problem, remember we use the non-negative orthant over the variable x. Let's look at a different example now, which is a bit more involved. So phase retrieval, what we want to do is for a 1D signal, we want to figure out what the phase is. And whenever you're trying to estimate, given some measurements of that 1D signal, we have to try and reconstruct that signal from some form in order to measure that reconstruction accuracy. So here A is defined as this 1D DFT matrix, and A is also what we use to solve this problem is this random illumination filter. So basically we just sample a bunch of points from a Gaussian distribution, and then that would construct this matrix A. And by doing so, it happens that we achieve perfect reconstruction for high probability of signals. And there are various lots of applications of doing this. Okay, so something that's in image processing, rank minimization. Again, it's a SDP problem. We want to minimize the rank of a matrix. However, this is a non-convex problem, so what we do is to minimize the trace, and that's a good way to relax this. So minimizing the trace of this positive semi-definite matrix X, subject to AX equals B, and then enforcing that positive semi-definite cone on the variable X. Here, I've added an additional constraint where all the entries are non-negative. So I've added also a non-negative orthant constraint on X. So the code looks like this. You can see I load the image here. This is a pretty expensive operation, so I do it patch by patch. So those are the coordinates given here. Construct the block matrices, denoise the image, and then pass it to the solver. And what we need to do is figure out where the image goes in this matrix X here. So we force X to take on these values in the yellow elements here. This has to be a symmetric matrix, so we just do the transpose and set those elements here as well. And all we need to do is to encode all this information is to just encode it in this lower triangular region here. What we know is that all we're really interested in are what these values are. These other values are just to fill in the matrix. And so when you run the optimization algorithm, this the trace of this matrix goes further and further down, and we get a denoised image. So it looks something like this. After 5 iterations, I just basically introduce these noisy pixels, which you can see here in yellow, and by running this algorithm, you can see that the more iterations, you get one that is close to recovering what was originally corrupted. Right, so next example, total variation reconstruction. So here again, we're given a 1D raw signal, and it's split into these 2 terms here. We've got one that is by the 2 norm, which is the, I think it's minimizing the difference between the signal and the one that is corrupted by noise, and we're trying to estimate the original signal. And then here, what we're trying to do with this L1 term is we're trying to penalize any significant variations in the signal itself. D is the 1D finite difference matrix. There's actually 2 ways you can solve this problem. We can see that this is an L2 norm, so naturally we might choose to use a SOCP constraint on this term, but in this case here, we can just add a square, and that converts it into a quadratic program. And then we can encode that in the matrix P. So yeah, there's applications include voice recognition and data transmission. A lot of code here. Yeah, I think you can see that it's a bit involved, but nevertheless, it's easy to create these matrices through functions. And you get these, a result that looks like this. You get the input signal and a reconstructed version of that signal that removes a lot of this volatility in the signal. So if you crank up lambda, you get a smoother and smoother signal, so cranking up this term here. And it only takes 2 seconds over 10 iterations, so it's very efficient. The last example is trajectory optimization. So this is using sum of squares programming, and here we want to minimize the jerk, or the third derivative of a polynomial. So a trajectory can be encoded as a sequence of polynomials, which is what we're doing here. We constrain that to the sum of squares cone, and then we set some initial conditions. So we say that the initial position is 0, the final position is 5 at time equals 1, and then we set the initial and final velocities to these values here. And so the polynomial, you can have any high order polynomial, and the higher the order of the polynomial, the better is the result. So, well, not technically, but you get something that is feasible. So if you come up with, if you put in something that is too low order, you may not find a feasible solution, so you just need to increase the order of the polynomial that you use, and in order to get something that's feasible. So sum of squares programming uses this idea of the lesser hierarchy. You may have heard of that, and it also goes by the name moment SOS. So the applications of this are path planning, UAVs, and robot manipulators. Okay, so the guts of the solver is to basically solve this KKT conditions. And for this cone quadratic program, we want to solve this, given this matrix K for these variables X, Y, and Z. So we know what K is, we know what this vector is, and the way to solve this is using a sequence of operations called the QR-Cholesky, which basically does QR and Cholesky on a lot of these terms. I'm not going to derive that here because it's pretty messy. If you look at the paper, it's pretty trivial, but it's a very effective way in having some level of numerical stability as you compute the solution vector. If you run out of memory, then you may want to look into iterative methods like minres. That's also implemented by this package here, and that falls into the set of methods called Krylov subspace methods. So things to consider, you want to consider scaling for numerical stability, the size of the problem that you're trying to solve. So I wouldn't recommend using this solver for very large scale problems or very highly sparse problems. This solver works pretty well when the problems are small and dense and where you need a high degree of accuracy. Another good thing is that because it's using matrix factorization, it's very easy to throw these to the GPU. And there's a GPU implementation of this solver as well. And you can get performance of up to 2 or 3 times faster by using that. So future work, there's a bit of additional GPU optimization required for the iterative methods that I've defined. There needs to be some integration with common optimization front ends like jump. More examples to make it more palatable to adopters in the scientific community, and just stabilizing the APIs so that it's ready for industrial applications. So in summary, what I found through this experience of developing this package is how tedious it is to define those matrices and vectors. I think one thing that the optimization community needs to focus on is just finding better abstractions for indexing into arrays and matrices, and just coming up with a language to express those constraints for any given optimization problem. Yeah, so that concludes the talk. Thanks for listening. Here's the QR code that will take you to the package. And you can read up the various documentation there. And yeah, looking forward to any PRs or any questions you may have. Thanks.
Yep. Are there any questions?
Hey, thanks for the talk. Did you do any benchmarking performance-wise against the Mosaic and the Sudemi packages?
That's a good question. I'm still yet to do that. Yeah.
Cool. And if there's no more questions, there is a keynote at the
Yeah, I wanted to remind everyone that at 4 o'clock, or really 4:10, in the main building, room 120, there's a keynote, another keynote. And also at 6 o'clock, there'll be the poster session. Let's thank Alexander again for a nice presentation.